So good. Okay, convert data to tensors and then to train and test splits. Nothing we haven't covered here before. So import torch, but it never hurts to practice code, right? Import torch from sklearn.model_selection. Import train test split so that we can split our red and blue dots randomly. And we're going to turn data into tensors. And we'll go x equals torch from numpy, and we'll pass in x here. And then we'll change it into type torch.float. Why do we do this? Well, because, oh my goodness, autocorrect. It's getting the best of me here. You're watching me live code this stuff and battle with autocorrect. That's what this whole course is. And am I really teaching PyTorch, or am I just battling with Google Colab's autocorrect? We are turning it into torch.float with a type here because why? NumPy's default, which is what Make Circles uses behind the scenes. NumPy is actually used in a lot of other machine learning libraries. Pandas, built on NumPy. Scikit-learn does a lot of NumPy. Matplotlib, NumPy. That's just showing the, what's the word? Is it ubiquitous? Ubiquity? I'm not sure, maybe. If not, you can correct me. The ubiquity of NumPy and test sets, but we're using PyTorch to leverage the power of autograd, which is what powers our gradient descent, and the fact that it can use GPUs. So we're creating train and test splits here with train test split x, y, and we're going to go test size equals 0.2, and we're going to set random state equals 42. And then we'll view our first 5 samples. Are these going to be tensors? Fingers crossed, we haven't got an error. Beautiful, we have tensors here. Okay, now we're up to the exciting part. We've got our data set back. I think it's time to build a model with nonlinearity. So if you'd like to peek ahead, check out TorchNN again. This is a little bit of a spoiler. Go into the nonlinear activations, see if you can find the one that we've already used. That's your challenge. Can you find the one we've already used? And go into here and search what is a nonlinear function. So give that a go and see what comes up. I'll see you in the next video. Welcome back. Now put your hand up if you're ready to learn about nonlinearity. And I know I can't see your hands up, but I better see some hands up, or I better feel some hands up, because my hand's up, because nonlinearity is a magic piece of the puzzle that we're about to learn about. So let's title this section, Building a Model with Nonlinearity. So just to re-emphasize, linear equals straight lines, and in turn, nonlinear equals non-straight lines. And I left off the end of the last video giving you the challenge of checking out the torch.nn module, looking for the nonlinear function that we've already used. Now, where would you go to find such a thing? And oh, what do we have in here? Nonlinear activations. And there's going to be a fair few things here, but essentially all of the modules within torch.nn are either some form of layer in a neural network, if we recall. Let's go to a neural network. We've seen the anatomy of a neural network. Generally, you'll have an input layer and then multiple hidden layers and some form of output layer. Well, these multiple hidden layers can be almost any combination of what's in torch.nn. And in fact, they can almost be any combination of function you could imagine. Whether they work or not is another question. But PyTorch implements some of the most common layers that you would have as hidden layers, and they might be pooling layers, padding layers, activation functions, and they all have the same premise. They perform some sort of mathematical operation on an input. And so if we look into the non-linear activation functions, you might have found nn.sigmoid. Where have we used this before? There's a sigmoid activation function in math terminology. It takes some input x, performs this operation on it, and here's what it looks like if we did it on a straight line. But I think we should put this in practice, and if you want an example, well, there's an example there. All of the other non-linear activations have examples as well, but I'll let you go through all of these in your own time. Otherwise, we're going to be here forever. nn.relu is another common function. We saw that when we looked at the architecture of a classification network. So with that being said, how about we start to code a classification model with non-linearity? And of course, if you wanted to, you could look up what is a non-linear function if you wanted to learn more. Non-linear means the graph is not a straight line. Oh, beautiful. So that's how I'd learn about non-linear functions. But while we're here together, how about we write some code? So let's go build a model with non-linear activation functions. And just one more thing before, just to re-emphasize what we're doing here. Before we write this code, I just remembered, I've got a nice slide, which is the question we posed in the previous video, the missing piece, nonlinearity. But the question I want you to think about is, what could you draw if you had an unlimited amount of straight, in other words, linear, and non-straight, non-linear lines? So we've seen previously that we can build a model, a linear model, to fit some data that's in a straight line, linear data. But when we're working with non-linear data, well, we need the power of non-linear functions. So this is circular data. And now this is only a 2D plot, keep in mind there. Whereas neural networks and machine learning models can work with numbers that are in hundreds of dimensions. Impossible for us humans to visualize, but since computers love numbers, it's a piece of cake to them. So from torch import nn, we're going to create our first neural network with nonlinear activations. This is so exciting. So let's create a class here. We'll create circle model. We've got circle model v1 already. We're going to create circle model v2. And we'll inherit from nn.module. And then we'll write the constructor, which is the init function. And we'll pass in self here. And then we'll go self, or super, sorry. Too many S words. Dot underscore underscore init underscore. There we go. So we've got the constructor here. And now let's create a layer 1. Self.layer1 equals just the same as what we've used before. nn.linear. We're going to create this quite similar to the model that we've built before, except with one added feature. And we're going to create in features, which is akin to the number of X features that we have here. Again, if this was different, if we had 3 X features, we might change this to 3. But because we're working with 2, we'll leave it as that. We'll keep out features as 10, so that we have 10 hidden units. And then we'll go layer 2. nn.linear. Again, these values here are very customizable because why? Because they're hyperparameters. So let's line up the out features of layer 2, and we'll do the same with layer 3. Because layer 3 is going to take the outputs of layer 2, so it needs in features of 10, and we want layer 3 to be the output layer, and we want one number as output, so we'll set 1 here. Now, here's the fun part. We're going to introduce a non-linear function. We're going to introduce the ReLU function. Now, we've seen sigmoid. ReLU is another very common one. It's actually quite simple, but let's write it out first. nn.ReLU. So remember, torch.nn stores a lot of existing nonlinear activation functions so that we don't necessarily have to code them ourselves. However, if we did want to code a ReLU function, let me show you. It's actually quite simple. If we dive into nn.ReLU, or ReLU, however you want to say it, I usually say ReLU, applies the rectified linear unit function element-wise. So that means element-wise on every element in our input tensor. And so it stands for rectified linear unit. And here's what it does. Basically, it takes an input. If the input is negative, it turns the input to 0, and it leaves the positive inputs how they are. And so this line is not straight. Now you could argue, yeah, well, it's straight here and then straight there, but this is a form of a non-linear activation function. So it goes zoom, boom. If it was linear, it would just stay straight there like that. But let's see it in practice. Do you think this is going to improve our model? Well, let's find out together, hey? Forward, we need to implement the forward method. And here's what we're going to do. Where should we put our nonlinear activation functions? So I'm just going to put a note here. ReLU is a nonlinear activation function. And remember, wherever I say function, it's just performing some sort of operation on a numerical input. So we're going to put a nonlinear activation function in between each of our layers. So let me show you what this looks like. Self.layer3. We're going to start from the outside in. Self.relu, and then we're going to go self.layer2. And then we're going to go self.relu. And then there's a fair bit going on here, but nothing we can't handle. Layer 1, and then here's the X. So what happens is our data goes into layer 1, performs a linear operation with nn.linear. Then we pass the output of layer 1 to a relu function. So where's relu up here? We turn all of the negative outputs of our model, of layer 1 to 0, and we keep the positives how they are. And then we do the same here with layer 2. And then finally, the outputs of layer 3 stay as they are. We've got out features there. We don't have a relu on the end here because we're going to pass the outputs to the sigmoid function later on. And if we really wanted to, we could put self.sigmoid here equals nn.sigmoid. But that's just one way of constructing it. We're just going to apply the sigmoid function to the logits of our model, because what are the logits? The raw output of our model. And so let's instantiate our model. This is going to be called model 3, which is a little bit confusing, but we're up to model 3, which is circle model v2. And we're going to send that to the target device. And then let's check model 3. What does this look like? Wonderful. So it doesn't actually show us where the relus appear, but it just shows us what are the parameters of our circle model v2. Now, I'd like you to have a think about this, and my challenge to you is to go ahead and see if this model is capable of working on our data, on our circular data. So we've got the data sets ready. You need to set up some training code. My challenge to you is write that training code and see if this model works. But we're going to go through that over the next few videos. And also, my other challenge to you is to go to the TensorFlow playground and recreate our neural network here. You can have 2 hidden layers. Does this go to 10? Well, it only goes to 8. We'll keep this at 5. So build something like this. So we've got 2 layers with 5. It's a little bit different to ours because we've got 2 layers with 10. And then put the learning rate to 0.01. Well, what do we have? 0.1 with stochastic gradient descent. We've been using 0.1, so we'll leave that. So this is the TensorFlow playground. And then change the activation here. Instead of linear, which we've used before, change it to relu, which is what we're using. And press play here and see what happens. I'll see you in the next video. Welcome back. In the last video, I left off leaving the challenge of recreating this model here. It's not too difficult to do. We've got 2 hidden layers and 5 neurons. We've got our data set, which looks kind of like ours. But the main points here are have to learning rate of 0.1, which is what we've been using. But to change it from, we've previously used a linear activation. To change it from linear to relu, which is what we've got set up here in the code. Now, remember, relu is a popular and effective nonlinear activation function. And we've been discussing that we need nonlinearity to model nonlinear data. And so that's the crux of what neural networks are. Artificial neural networks, not to get confused with the brain neural networks, but who knows? This might be how they work too. I don't know, I'm not a neurosurgeon or a neuroscientist. Artificial neural networks are a large combination of linear, so this is straight, and non-straight, non-linear functions, which are potentially able to find patterns in data. And so for our data set, it's quite small. It's just a blue and a red circle, but this same principle applies for larger data sets and larger models, combined linear and non-linear functions. So we've got a few tabs going on here. Let's get rid of some. Let's come back to here. Did you try this out? Does it work? Do you think it'll work? I don't know. Let's find out together. Ready? 3, 2, 1. Look at that! Almost instantly, the training loss goes down to 0 and the test loss is basically 0 as well. Look at that. That's amazing. We can stop that there. And if we change the learning rate maybe a little lower, let's see what happens. it takes a little bit longer to get to where it wants to go to. See, that's the power of changing the learning rate. Let's make it really small. What happens here? So that was about 300 epochs. The loss started to go down. If we change it to be really small, oh, we're getting a little bit of a trend. Is it starting to go down? We're already surpassed the epochs that we had. So see how the learning rate is much smaller? That means our model is learning much slower. So this is just a beautiful visual way of demonstrating different values of the learning rate. We could sit here all day and that might not get to lower, but let's increase it by 10x. And that was over 1,000 epochs and it's still at about 0.5, let's say. Oh, we got a better, oh, we're going faster already. So not even at 500 or so epochs, we're about 0.4. That's the power of the learning rate. We'll increase it by another 10x. We'll reset, start again. Oh, would you look at that? Much faster this time. That is beautiful. Oh, there's nothing better than watching a loss curve go down. In the world of machine learning, that is. And then we reset that again. And let's change it right back to what we had. And we get to 0 in basically under 100 epochs. So that's the power of the learning rate. Little visual representation. Speaking of learning rates, it's time for us to build an optimizer and a loss function. So let's write here. We've got our nonlinear model. Set up, loss, and optimizer. You might have already done this because the code, this is code that we've written before, but we're going to redo it for completeness and practice. So we want a loss function. We're working with logits here, and we're working with binary cross entropy. So what loss do we use? Binary cross entropy. Sorry, we're working with a binary classification problem. Blue dots or red dots. Torch.optim. What are some other binary classification problems that you can think of? We want model 3 dot parameters. They're the parameters that we want to optimize this model here. And we're going to set our LR to 0.1, just like we had in the TensorFlow playground. Beautiful. So some other binary classification problems I can think of would be email, spam or not spam, credit cards, so equals fraud or not fraud. What else? You might have insurance claims equals who's at fault or not at fault. If someone puts in a claim speaking about a car crash, whose fault was it? Was the person submitting the claim, were they at fault? Or was the person who was also mentioned in the claim, are they not at fault? So there's many more, but they're just some I can think of off the top of my head. But now let's train our model with nonlinearity. Woohoo! Oh, we're on a roll here. Training a model with nonlinearity. So we've seen that if we introduce a nonlinear activation function within a model, remember this is a linear activation function, and if we train this, the loss doesn't go down. But if we just adjust this to add a ReLU in here, we get the loss going down. So hopefully this replicates with our pure PyTorch code. So let's do it, hey? So we're going to create random seeds. Because we're working with CUDA, we'll introduce the CUDA random seed as well. Torch.manual seed. Again, don't worry too much if your numbers on your screen aren't exactly what mine are. That's due to the inherent randomness of machine learning. In fact, stochastic gradient descent, stochastic again stands for random. We're just setting up the seeds here so that they can be as close as possible, but the direction is more important. So if my loss goes down, your loss should also go down. On target device, and then we're going to go xtrain. So this is setting up device agnostic code. We've done this before, but we're going to do it again for completeness, just to practice every step of the puzzle. That's what we want to do. We want to have experience. That's what this course is. It's a momentum builder, so that when you go to other repos and machine learning projects that use PyTorch, you can go, oh, does this code set device agnostic code? What problem are we working on? Is it binary or multi-class classification? So let's go loop through data. Again, we've done this before, but we're going to set up the epochs. Let's do 1,000 epochs, why not? So we can go for epoch in range epochs. What do we do here? Well, we want to train. So this is training code. We set our model, model3.train. And I want you to start to think about how could we functionize this training code. We're going to start to move towards that in a future video. So one is forward pass. We've got the logits. Why the logits? Well, because the raw output of our model without any activation functions towards the final layer, classified as logits or called logits. And then we create ypred, as in prediction labels, by rounding the output of torch.sigmoid of the logits. So this is going to take us from logits to prediction probabilities to prediction labels. And then we can go to, which is calculate the loss. That's from my unofficial PyTorch song. Calculate the loss. We go loss equals loss fn, y logits. Because remember, we've got BCE with logits loss and takes in logits as first input. And that's going to calculate the loss between our model's logits and the y training labels. And we will go here, we'll calculate accuracy using our accuracy function. And this one is a little bit backwards compared to PyTorch, but we pass in the y training labels first, but it's constructed this way because it's in the same style as scikit-learn. 3, we go optimizer 0 grad. We zero the gradients of the optimizer so that it can start from fresh, calculating the ideal gradients every epoch. So it's going to reset every epoch, which is fine. Then we're going to perform backpropagation. PyTorch is going to take care of that for us by calling loss backwards. And then we will perform gradient descent. So step the optimizer to see how we should improve our model parameters. So optimizer.step. Oh, and I want to show you, speaking of model parameters, let's check our model3.stateDict. So the relu activation function actually doesn't have any parameters. So you'll notice here, we've got weight, we've got bias of layer 1, layer 2, and a layer 3. So the relu function here doesn't have any parameters to optimize. If we go nn.relu, does it say what it implements? There we go. So it's just the maximum of 0 or x. So it takes the input and takes the max of 0 or x. And so when it takes the max of 0 or x, if it's a negative number, 0 is going to be higher than a negative number. So that's why it zeros all of the negative inputs. And then it leaves the positive inputs how they are, because the max of a positive input versus 0 is the positive input. So this has no parameters to optimize. That's why it's so effective, because you think about it, every parameter in our model needs some little bit of computation to adjust. And so the more parameters we add to our model, the more compute that is required. So generally, the kind of trade-off in machine learning is that, yes, more parameters have more of an ability to learn, but you need more compute. So let's go model3.eval, and we're going to go with torch.inference mode. If I could spell inference, that'd be fantastic. We're going to do what? We're going to do the forward pass. So test logits equals model3 on the test data. And then we're going to calculate the test pred labels by calling torch.round on torch.sigmoid on the test logits. And then we can calculate the test loss. How do we do that? Equals loss fn on test logits versus y test. And then we can also calculate the test accuracy. I'm just going to give myself some more space here so I can code in the middle of the screen. Equals accuracy function on what? We're going to pass in y true equals y test. And then we will pass in y pred equals test pred. Beautiful. A final step here is to print out what's happening. Now, this will be very important because, one, it's fun to know what your model's doing, and two, if our model does actually learn, I'd like to see the loss values go down and the accuracy values go up. As I said, there's nothing much more beautiful in the world of machine learning than watching a loss function go down, or a loss value go down, and watching a loss curve go down. So let's print out the current epoch, and then we'll print out the loss, which will just be the training loss, and we'll take that to 4 decimal places. and then we'll go accuracy here, and this will be acc, and we'll take this to 2 decimal places, and we'll put a little percentage sign there, and then we'll break it up by putting in the test loss here, and we'll put in the test loss, because remember, our model learns patterns on the training data set and then evaluates those patterns on the test data set. So, and we'll pass in test acc here. And no doubt there might be an error or two within all of this code, but we're going to try and run this because we've seen this code before, but I think we're ready. We're training our first model here with non-linearities built into the model. You ready? 3, 2, 1, let's go. Oh, of course. Module torch CUDA has no attribute manuals are. Just a typo. Standard manual. There we go. Had to sound that out. Another one. What do we get wrong here? Oh, target size must be same as input size. Where did it mess up here? What do we get wrong? Test loss, test logits on Y test. So these two aren't matching up. Model 3 X test and Y test. What's the size of... So let's do some troubleshooting on the fly, hey? Not everything always works out as you want. So length of X test, we've got a shape issue here. Remember how I said one of the most common issues in deep learning is a shape issue? So we've got the same shape here. Let's check test logits.shape and ytest.shape. We'll print this out. So 200, oh, here's what we have to do. That's what we missed, dot squeeze. Ah, see how I've been hinting at the fact that we needed to call dot squeeze? So this is where the discrepancy is. Our test logits.shape, we've got an extra dimension here. And what are we getting here? A value error on the target size, which is a shape mismatch. So we've got target size 200, must be the same input size as torch size 201. So, did we squeeze this? Oh, that's why the training worked. Okay, so we've missed this. Let's just get rid of this. So we're getting rid of the extra 1 dimension by using squeeze, which is the 1 dimension here. We should have everything lined up. There we go. Okay, oh, look at that. Yes. Our accuracy has gone up, albeit not by too much. It's still not perfect. Ideally, we'd like this to be towards 100% and the loss to be lower. But I feel like we've got a better performing model. Don't you? Now that is the power of non-linearity. All we did was we added in a ReLU layer, or just 2 of them. ReLU here, ReLU here. But what did we do? We gave our model the power of straight lines, straight linear, of straight lines, and non-straight lines. So it can potentially draw a line to separate these circles. So in the next video, let's draw a line, plot our model's decision boundary using our function, and see if it really did learn anything. I'll see you there. Welcome back. In the last video, we trained our first model, and as you can tell, I've got the biggest smile on my face, but we trained our first model that harnesses both the power of straight lines and non-straight lines, or linear functions and non-linear functions. And by the 1000th epoch, we look like we're getting a bit better results than just pure guessing, which is 50%, because we have 500 samples of red dots and 500 samples of blue dots. So we have evenly balanced classes. Now, we've seen that if we added a ReLU activation function with a dataset similar to ours with a TensorFlow playground, the model starts to fit, but it doesn't work with just linear. There's a few other activation functions that you could play around with here. You could play around with the learning rate, regularization. If you're not sure what that is, I'll leave that as extra curriculum to look up. But we're going to retire the TensorFlow playground for now because we're going to go back to writing code. So let's get out of that, and let's get out of that. We now have to evaluate our model because right now it's just numbers on a page. So let's write down here, 6.4. What do we like to do to evaluate things? It's visualize, visualize, visualize. So evaluating a model trained with nonlinear activation functions. And we also discussed the point that neural networks are really just a big combination of linear and nonlinear functions trying to draw patterns in data. So with that being said, let's make some predictions with our Model 3, our most recently trained model. We'll put it into eval mode, and then we'll set up inference mode. Inference mode, beautiful. And then we'll go ypreds equals torch.round, and then torch.sigmoid. We could functionize this, of course. Model 3, and then pass in xtest. And you know what? We're going to squeeze these here because we ran into some troubles in the previous video. I actually really liked that we did, because then we got to troubleshoot a shape error on the fly, because that's one of the most common issues you're going to come across in deep learning. So ypreds, let's check them out, and then let's check out ytest. We want ytest 10. So remember, when we're evaluating predictions, we want them to be in the same format as our original labels. We want to compare apples to apples. And if we compare the format here, do these two things look the same? Yes, they do. They're both on CUDA, and they're both floats. We can see that it's got this one wrong, whereas the other ones look pretty good. This might look pretty good if we visualize it. So now you might have already done this, because I issued the challenge of plotting the decision boundaries. Plot decision boundaries, and let's go plt.figure. And we're going to set up the fig size to equal 12.6, because, again, one of the advantages of hosting a machine learning cooking show is that you can code ahead of time. And then we can go plt.title is train. And then we're going to call our plot decision boundary function, which we've seen before, plot decision boundary. And we're going to pass this one in. We could do model 3. But we could also pass it in our older models too, Model 1, that doesn't use nonlinearity. In fact, I reckon that'll be a great comparison. So we'll also create another plot here for the test data, and this will be on index number 2. So remember, subplot is number of rows, number of columns, index where the plot appears. We'll give this one a title, plot.title. This will be test, and Google Colab, I didn't want that. As I said, this course is also a battle between me and Google Colab's autocorrect. So we'll go Model 3, and we'll pass in the test data here. And behind the scenes, our plot decision boundary function will create a beautiful graphic for us, perform some predictions on the features input, and then we'll compare them with the Y values. Let's see what's going on here. Oh, look at that! Yes, our first nonlinear model. Okay, it's not perfect, but it is certainly much better than the models that we had before. Look at this. Model 1 has no linearity. Model 1 equals no nonlinearity. I've got a double negative there. Whereas Model 3 equals has nonlinearity. So do you see the power of nonlinearity, or better yet, the power of linearity or linear straight lines with non-straight lines? So I feel like we could do better than this though. Here's your challenge, is can you improve Model 3 to do better? What did we get? 79% accuracy. To do better than 80% accuracy on the test data. I think you can. So that's the challenge. And if you're looking for hints on how to do so, where can you look? Well, we've covered this, improving a model. So maybe you add some more layers. Maybe you add more hidden units. Maybe you fit for longer. Maybe if you add more layers, you put a ReLU activation function on top of those as well. Maybe you lower the learning rate, because right now we've got 0.1. So give this a shot. Try and improve it. I think you can do it. But we're going to push forward. That's going to be your challenge for some extra curriculum. I think in the next section, we've seen our nonlinear activation functions in action. Let's write some code to replicate them. I'll see you there. Welcome back. In the last video, I left off with the challenge of improving Model 3 to do better than 80% accuracy on the test data. I hope you gave it a shot, but here are some of the things I would have done. Is I potentially add more layers, and maybe increase the number of hidden units, and then if we needed to, fit for longer, and maybe lower the learning rate to 0.01. But I'll leave that for you to explore, because that's the motto of the data scientist, right? Is to experiment, experiment, experiment. So let's go in here. We've seen our nonlinear activation functions in practice. Let's replicate them. So replicating nonlinear activation functions. And remember, neural networks, rather than us telling the model what to learn, we give it the tools to discover patterns in data, and it tries to figure out the best patterns on its own. And what are these tools? Let's write down here. We've seen this in action. And these tools are linear and non-linear functions. So a neural network is a big stack of linear and non-linear functions. For us, we've only got about 4 layers or so, 4 or 5 layers. But as I said, other networks can get much larger. But the premise remains, some form of linear and non-linear manipulation of the data. So let's get out of this. Let's make our workspace a little bit more cleaner. Replicating nonlinear activation functions. So let's create a tensor to start with. Everything starts from the tensor. And we'll go A equals torch, a range. And we're going to create a range from -10 to 10 with a step of 1. And we can set the D type here to equal torch.float32, but we don't actually need to. That's going to be the default. So if we set A here, A.D type, then we've got torch float32, and I'm pretty sure if we got rid of that, oh, we've got torch int64. Why is that happening? Well, let's check out A. Oh, it's because we've got integers as our values, because we have a step as 1. If we turn this into a float, what's going to happen? We get float32, but we'll keep it, otherwise this is going to be what, about 100 numbers? Yeah, nah, that's too many. Let's keep it at -10 to 10, and we'll set the D type here to torch float32. Beautiful. So it looks like PyTorch's default data type for integers is int64, but we're going to work with float32 because float32, if our data wasn't float32, with the functions we're about to create, we might run into some errors. So let's visualize this data. I want you to guess, is this a straight line or non-straight line? You've got 3 seconds. 1, 2, 3. Straight line. There we go. We've got -10 to +10 up here, or 9. Close enough. And so how would we turn this straight line? If it's a straight line, it's linear. How would we perform the ReLU activation function on this? Now, we could, of course, call torch ReLU on A. Actually, let's in fact just plot this. plt.plot on torch ReLU. What does this look like? Boom, there we go. But we want to replicate the ReLU function. So let's go nn.ReLU. What does it do? We've seen this before. So we need the max, we need to return, based on an input, we need the max of 0 and x. So let's give it a shot. We'll come here. Again, we need more space. There can never be enough code space here. I like writing lots of code. I don't know about you. But let's go ReLU. We'll take an input x, which will be some form of tensor, and we'll go return torch.maximum. I think you could just do torch.max, but we'll try maximum. Torch.tensor 0. So the maximum is going to return the max between whatever this is, one option, and whatever the other option is. So inputs must be tensors. So maybe we could just give a type hint here that this is torch.tensor. And this should return a tensor too. Return torch.tensor. Beautiful. You ready to try it out? Let's see what our ReLU function does. ReLU A. Wonderful. It looks like we got quite a similar output to before. Here's our original A. So we've got negative numbers. There we go. So recall that the ReLU activation function turns all negative numbers into 0 because it takes the maximum between 0 and the input. And if the input's negative, well then 0 is bigger than it. And it leaves all of the positive values as they are. So that's the beauty of ReLU. Quite simple, but very effective. So let's plot ReLU activation function, our custom one. We will go plt.plot. We'll call our ReLU function on A. Let's see what this looks like. Oh, look at us go. Well done. Just the exact same as the torch relu function. Easy as that, hey? And what's another nonlinear activation function that we've used before? Well, I believe one of them is, if we go down to here, what did we say before? Sigmoid, where is that? Where are you, Sigmoid? Here we go. Hello, Sigmoid. Ooh, this has got a little bit more going on here. 1 over 1 plus exponential of negative x. So sigmoid, or this little symbol for sigmoid, of x, which is an input, we get this. So let's try and replicate this. I might just bring this one in here. Right, now let's do the same for sigmoid. So what do we have here? Well, we want to create a custom sigmoid, and we want to have some sort of input, x, and we want to return 1 divided by, do we have the function in sigmoid? 1 divided by 1 plus exponential, 1 plus torch.exp for exponential on negative x. And we might put the bottom side in brackets so that it does that operation. I reckon that looks all right to me. So 1 divided by 1 plus torch exponential of negative x. Do we have that? Yes, we do. Well, there's only one real way to find out. Well, let's plot the torch version of sigmoid. Torch.sigmoid, and we'll pass in x. See what happens. And then, oh, we have a. My bad. A is our tensor. What do we get? We get a curved line. Wonderful. And then we go plt.plot, and we're going to use our sigmoid function on a. Did we replicate torch's sigmoid function? Yes, we did. Woohoo! Now, see, this is what's happening behind the scenes with our neural networks. Of course, you could do more complicated activation functions or layers and whatnot, and you can try to replicate them. In fact, that's a great exercise to try and do. But we've essentially, across the videos and the sections that we've done, we've replicated our linear layer and we've replicated the ReLU. So we've actually built this model from scratch, or we could if we really wanted to, but it's a lot easier to use PyTorch's layers because we're building neural networks here like Lego bricks, stacking together these layers in some way, shape, or form. And because they're a part of PyTorch, we know that they've been error tested and they compute as fast as possible behind the scenes and use GPU, and we get a whole bunch of benefits. PyTorch offers a lot of benefits by using these layers rather than writing them ourselves. And so this is what our model is doing. It's literally like to learn these values and decrease the loss function and increase the accuracy. It's combining linear layers and nonlinear layers or nonlinear functions. Where's our ReLU function? Here. A ReLU function like this behind the scenes. So just combining linear and nonlinear functions to fit a data set. And that premise remains even on our small data set and on very large data sets and very large models. So with that being said, I think it's time for us to push on. We've covered a fair bit of code here, but we've worked on a binary classification problem. Have we worked on a multi-class classification problem yet? Do we have that here? Where's my fun graphic? We have multi-class classification. I think that's what we cover next. We're going to put together all of the steps in our workflow that we've covered for binary classification. But now let's move on to a multi-class classification problem. If you're with me, I'll see you in the next video. Welcome back. In the last few videos, we've been harnessing the power of nonlinearity, specifically non-straight line functions, and we replicated some here. And we learned that a neural network combines linear and non-linear functions to find patterns in data. And for our simple red versus blue dots, once we added a little bit of non-linearity, we found the secret sauce to start separating our blue and red dots. And I also issued you the challenge to try and improve this, and I think you can do it. So hopefully you've given that a go. But now let's keep pushing forward. We're going to reiterate over basically everything that we've done, except this time from the point of view of a multi-class classification problem. So I believe we're up to section 8, putting it all together with a multi-class classification problem. Beautiful. And recall the difference between binary classification equals one thing, or another, such as cat versus dog, if you were building a cat versus dog image classifier, spam versus not spam for, say, emails that were spam or not spam, or even internet posts on Facebook or Twitter or one of the other internet services, and then fraud or not fraud for credit card transactions, and then multi-class classification is more than one thing or another. So we could have cat versus dog versus chicken. So I think we've got all the skills to do this. Our architecture might be a little bit different for a multi-class classification problem, but we've got so many building blocks now, it's not funny. Let's clean up this and we'll add some more code cells. And just to reiterate, so we've gone over nonlinearity. The question is, what could you draw if you had an unlimited amount of straight, linear, and non-straight, non-linear lines? I believe you could draw some pretty intricate patterns, and that is what our neural networks are doing behind the scenes. And so we also learned that if we wanted to just replicate some of these nonlinear functions, some of the ones that we've used before, we could create a range. Linear activation is just the line itself. And then if we wanted to do sigmoid, we get this curl here. And then if we wanted to do relu, well, we saw how to replicate the relu function as well. These both are nonlinear. And of course, torch.nn has far more nonlinear activations where they came from, just as it has far more different layers. And you'll get used to these with practice, and that's what we're doing here. So let's go back to the keynote. So this is what we're going to be working on, multi-class classification. So there's one of the big differences here. We use the softmax activation function versus sigmoid. There's another big difference here. Instead of binary cross entropy, we use just cross entropy. But I think most of it's going to stay the same. We're going to see this in action in a second, but let's just describe our problem space. Just to go visual, we've covered a fair bit here. Well done, everyone. So binary versus multi-class classification. Binary, one thing or another, 0 or 1. Multi-class could be 3 things, could be 1,000 things, could be 5,000 things, could be 25 things. So more than one thing or another. But that's the basic premise we're going to go with. Let's create some data, hey? 8.1. Creating a toy multi-class dataset. And so to create our dataset, we're going to import our dependencies. We're going to re-import torch, even though we already have it, just for a little bit of completeness. And we're going to go matplotlib. So we can plot. As always, we like to get visual where we can. Visualize, visualize, visualize. We're going to import from scikit-learn.datasets. Let's get make blobs. Now, where would I get this from? So sklearn.datasets, what do we get? Toy datasets. Do we have classification? Toy datasets. Do we have blobs? If we just go make scikit-learn classification datasets. What do we get? Here's one option. There's also make blobs. Beautiful. Make blobs. This is the code for that. So let's just copy this in here and make blobs. We're going to see this in action anyway. Make blobs. As you might have guessed, it makes some blobs for us. I like blobs. It's a fun word to say. Blobs. So we want train, test, split because we want to make a data set and then we want to split it into train and test. Let's set the number of hyperparameters. So set the hyperparameters for data creation. Now I got these from the documentation here. Number of samples, how many blobs do we want? How many features do we want? So say for example, we wanted 2 different classes. That would be binary classification. Say for example, you wanted 10 classes, you could set this to 10. And we're going to see what the others are in practice. But if you want to read through them, you can well and truly do that. So let's set up. We want num classes. Let's double what we've been working with. We've been working with 2 classes, red dots or blue dots. Let's step it up a notch. We'll go to 4 classes. Watch out, everyone. And we're going to go number of features will be 2. So we have the same number of features. And then the random seed is going to be 42. You might be wondering why these are capitalized. Well, generally, if we do have some hyperparameters that we say set at the start of a notebook, you'll find it's quite common for people to write them as capital letters just to say that, hey, these are some settings that you can change. You don't have to, but I'm just going to introduce that anyway because you might stumble upon it yourself. So create multi-class data. We're going to use the make blobs function here. So we're going to create some X blobs, some feature blobs, and some label blobs. We'll see what these look like in a second. I know I'm just saying blobs a lot, but we pass in here, none samples. How many do we want? Let's create 1,000 as well. That could really be a hyperparameter, but we'll just leave that how it is for now. Number of features is going to be num features. Centers equals num classes. So we're going to create 4 classes because we've set up num classes equal to 4. And then we're going to go center standard deviation. We'll give them a little shake up, add a little bit of randomness in here. Give the clusters a little shake up. We'll mix them up a bit, make it a bit hard for our model. But we'll see what this does in a second. Random state equals random seed, which is our favorite random seed, 42. Of course, you can set it whatever number you want, but I like 42. Oh, and we need a comma here, of course. Beautiful. Now, what do we have to do here? Well, because we're using scikit-learn, and scikit-learn leverages NumPy, so let's turn our data into tensors. Turn data into tensors, and how do we do that? Well, we grab xblob, and we call torch from NumPy. From NumPy, if I could type, that would be fantastic. That's all right. We're doing pretty well today. Haven't made too many typos. We did make a few in a couple of videos before, but hey, I'm only human. So we're going to torch from NumPy, and we're going to pass in the y blob, and we'll turn it into torch.float because remember NumPy defaults as float 64, whereas pytorch likes float 32. So split into training and test, and we're going to create xblob train, y or x test, xblob test. We'll keep the blob nomenclature here, y blob train and y blob test. And here's again where we're going to leverage the train test split function from scikit-learn. So thank you for that, scikit-learn. Xblob, and we're going to pass the y blob, so features, labels, x is the features, y are the labels, and a test size. We've been using a test size of 20%. That means 80% of the data will be for the training data. That's a fair enough split with our data set. And we're going to set the random seed to random seed because normally train test split is random, but because we want some reproducibility here, we're passing random seeds. Finally, we need to get visual. So let's plot the data. Right now we've got a whole bunch of code and a whole bunch of talking, but not too much visuals going on. So we'll write down here, visualize, visualize, visualize. And we can call in plot.figure. What size do we want? I'm going to use my favorite hand in poker, which is 10:7, because it's generally worked out to be a good plot size for, in my experience anyway. We'll go xblob, and we want the 0th index here, and then we'll grab xblob as well. And you might notice that we're visualizing the whole data set here. That's perfectly fine. We could visualize train and test separately if we really wanted to, but I'll leave that as a little challenge to you. And we're going to go red, yellow, blue. Wonderful. What did we get wrong? Oh, of course we got something wrong. Center STD. Did we spell center wrong? Cluster STD. That's what I missed. So cluster STD. Standard deviation. What do we get wrong? Random seed. Oh, this needs to be random state. Oh, another typo. You know what? Just as I said I wasn't getting too many typos, I get 3. There we go. Look at that. Our first multi-class classification data set. So if we set this to 0, what does it do to our clusters? Just take note of what's going on here, particularly the space between all of the dots. Now, if we set this cluster STD to 0, what happens? We get dots that are really just, look at that. That's too easy. Let's mix it up, all right? Now, you can pick whatever value you want here. I'm going to use 1.5 because now we need to build a model that's going to draw some lines between these 4 colors, 2 axes, 4 different classes. But it's not going to be perfect because we've got some red dots that are basically in the blue dots. And so, what's our next step? Well, we've got some data ready. It's now time to build a model. So, I'll see you in the next video. Let's build our first multi-class classification model. Welcome back. In the last video, we created a multi-class classification dataset using scikit-learn's makeBlobs function. And now, why are we doing this? Well, because we're going to put all of what we've covered so far together. But instead of using binary classification or working with binary classification data, we're going to do it with multi-class classification data. So with that being said, let's get into building a multi-class classification model. So we'll create a little heading here. Building a multi-class classification model in PyTorch. And now I want you to have a think about this. We spent the last few videos covering nonlinearity. Does this data set need nonlinearity? As in, could we separate this data set with pure straight lines? Or do we need some non-straight lines as well? Have a think about that. It's okay if you're not sure. We're going to be building a model to fit this data anyway, or draw patterns in this data anyway. And now, before we get into coding a model, so for multi-class classification, we've got this. For the input layer shape, we need to define the in features. So how many in features do we have? For the hidden layers, well, we could set this to whatever we want, but we're going to keep it nice and simple for now. For the number of neurons per hidden layer, again, this could be almost whatever we want, but because we're working with a relatively small data set, we've only got 4 different classes, we've only got 1,000 data points, we'll keep it small as well, but you could change this. Remember, you can change any of these because they're hyperparameters. For the output layer shape, well, how many output features do we want? We need 1 per class. How many classes do we have? We have 4 clusters of different dots here, so we'll need 4 output features. And then if we go back, we have an output activation of softmax. We haven't seen that yet. And then we have a loss function. Rather than binary cross entropy, we have cross entropy. And then optimizer as well is the same as binary classification. 2 of the most common are SGD, stochastic gradient descent, or the atom optimizer. But of course, the torch.optim package has many different options as well. So let's push forward and create our first multi-class classification model. First, we're going to get into the habit of creating device agnostic code. And we'll set the device here, equals CUDA. Nothing we haven't seen before, but again, we're doing this to put it all together so that we have a lot of practice. Is available, else CPU, and let's go device. So we should have a GPU available. Beautiful, CUDA. Now, of course, if you don't, you can go change runtime type, select GPU here. That will restart the runtime. You'll have to run all of the code that's before this cell as well, but I'm going to be using a GPU. You don't necessarily need one because our data set's quite small and our models aren't going to be very large, but we set this up so we have device agnostic code. And so let's build a multi-class classification model. Ooh, look at us go. Just covering all of the foundations of classification in general here. And we now know that we can combine linear and nonlinear functions to create neural networks that can find patterns in almost any kind of data. So I'm going to call my class here blob model, and it's going to, of course, inherit from nn.module. And we're going to upgrade our class here. We're going to take some inputs here, and I'll show you how to do this. If you're familiar with Python classes, you would have already done stuff like this, but we're going to set some parameters for our models, because as you write more and more complex classes, you'll want to take inputs here. And I'm going to preset the hidden units parameter to 8. Because I've decided, you know what, I'm going to start off with 8 hidden units, and if I wanted to change this to 128, I could. But in the constructor here, we've got some options. So we have input features. We're going to set these programmatically as inputs to our class when we instantiate it. The same with output features as well. And so here we're going to call self, oh no, super, sorry. I always get this mixed up. .init and underscore underscore. Beautiful. So we could do a doc string here as well. So let's write in this. Initializes multi-class classification. If I could spell classification model. Oh, this is great. And then we have some args here. This is just a standard way of writing doc strings. If you want to find out, this is Google Python docstring guide. There we go, Google Python style guide. This is where I get mine from. You can scroll through this. This is just a way to write Python code. Yeah, there we go. So we've got a little sentence saying what's going on. We've got args, we've got returns, and we've got errors if something's going on. So I highly recommend checking that out. Just a little tidbit. So this is if someone was to use our class later on, they know what the input features are. Input features, which is an int, which is number of input features to the model. And then, of course, we've got output features, which is also an int, which is number of output features of the model. And we've got the red line here is telling us we've got something wrong, but that's okay. And then the hidden features, oh, well, this is number of output classes for the case of multi-class classification. And then the hidden units, int, and then number of hidden units between layers. And then the default is 8. Beautiful. And then under that, we'll just do that. Is that going to fix itself? Yeah, there we go. We could put in what it returns, whatever it returns, and then an example use case, but I'll leave that for you to fill out if you like. So let's instantiate some things here. What we might do is write self.linear layer stack, self.linear layer stack, and we will set this as nn.sequential. Ooh, we haven't seen this before, but we're just going to look at a different way of writing a model here. Previously, when we created a model, what did we do? Well, we instantiated each layer as its own parameter here, and then we called on them one by one, but we did it in a straightforward fashion. So that's why we're going to use sequential here to just step through our layers. We're not doing anything too fancy, so we'll just set up a sequential stack of layers here. And recall that sequential just steps through, passes the data through each one of these layers one by one, and because we've set up the parameters up here, input features can equal to input features, and output features. What is this going to be? Is this going to be output features, or is this going to be hidden units? It's going to be hidden units because it's not the final layer. We want the final layer to output our output features. So input features, this will be hidden units because remember, the subsequent layer needs to line up with the previous layer. Output features, we're going to create another one that outputs hidden units, and then we'll go nn.linear. In features equals hidden units because it takes the output features of the previous layer. So as you see here, the output features of this feeds into here. The output features of this feeds into here. And then finally, this is going to be our final layer. We'll do 3 layers. Output features equals output features. Wonderful. So how do we know the values of each of these? Well, let's have a look at xtrain.shape and ytrain.shape. So in the case of X, we have 2 input features, and in the case of Y, well, this is a little confusing as well because Y is a scalar, but what do you think the values for Y are going to be? Well, let's go np, or is there torch.unique? I'm not sure. Let's find out together, hey? Torch unique, 0 and 1, ytrain. Oh, we need yblob train, that's right, blog. I'm too used to writing blob. And we need blob train, but I believe it's the same here. And then blob There we go. So we have 4 classes, so we need an output features value of 4. And now if we wanted to add nonlinearity here, we could put it in between our layers here like this. But I asked the question before, do you think that this data set needs nonlinearity? Well, let's leave it in there to begin with. And one of the challenges for you, do we need commas here? I think we need commas here. One of the challenges for you will be to test the model with nonlinearity and without nonlinearity. So let's just leave it in there for the time being. What's missing from this? Well, we need a forward method. So def forward self x. What can we do here? Well, because we've created this as a linear layer stack using nn.sequential, we can just go return linear layer stack and pass it x, and what's going to happen? Whatever input goes into the forward method is just going to go through these layers sequentially. Oh, we need to put self here because we've initialized it in the constructor. Beautiful. And now let's create an instance of blob model and send it to the target device. We'll go model 4 equals blob model, and then we can use our input features parameter, which is this one here, and we're going to pass it a value of what? 2, and then output features. Why? Because we have 2 X features. Now the output features is going to be the same as the number of classes that we have. 4. If we had 10 classes, we'd set it to 10. So we'll go 4, and then the hidden units is going to be 8 by default. So we don't have to put this here, but we're going to put it there anyway. And then of course, we're going to send this to device, and then we're going to go model 4. What did we get wrong here? Unexpected keyword argument. Output features. Did we spell something wrong? No doubt we've got a spelling mistake. Output features. Output features? Oh, out features. Ah. That's what we needed. Out features, not output. I got a little confused there. Okay. There we go. Okay, beautiful. So just recall that the parameter here for nn.linear, did you pick up on that? Is out features, not output features. Output features, a little confusing here, is our final layer, our output layers, number of features there. So we've now got a multi-class classification model that lines up with the data that we're using. So the shapes line up. Beautiful. Well, what's next? Well, we have to create a loss function and, of course, a training loop. So I'll see you in the next few videos, and let's do that together. Welcome back. In the last video, we created our multi-class classification model, and we did so by subclassing nn.module, and we set up a few parameters for our class constructor here, so that when we made an instance of the blob model, we could customize the input features, the output features. Remember, this lines up with how many features X has, and the output features here lines up with how many classes are in our data. So if we had 10 classes, we could change this to 10 and it would line up. And then if we wanted 128 hidden units, well, we could change that. So we're getting a little bit more programmatic with how we create models here. And as you'll see later on, a lot of the things that we've built in here can also be functionized in a similar manner. But let's keep pushing forward. What's our next step? If we build a model, if we refer to the workflow, you'd see that we have to create a loss function and an optimizer for a multi-class classification model. And so what's our option here for creating a loss function? Where do we find loss functions in PyTorch? I'm just going to get out of this and I'll make a new tab here. And if we search torch.nn, because torch.nn is the basic building blocks for graphs, in other words, neural networks, where do we find loss functions? Here we go. Beautiful. So we've seen that L1 loss or MSE loss could be used for regression, predicting a number. And I'm here to tell you as well that for classification, we're going to be looking at cross-entropy loss. Now, this is for multi-class classification. For binary classification, we work with BCE loss. And of course, there's a few more here, but I'm going to leave that as something that you can explore on your own. Let's jump in to cross-entropy loss. So what do we have here? This criterion computes. Remember, a loss function in PyTorch is also referred to as a criterion. You might also see loss function referred to as cost function, C-O-S-T, but I call them loss functions. So this criterion computes the cross-entropy loss between input and target. Okay, so the input is something, and the target is our target labels. It is useful when training a classification problem with C classes. There we go. So that's what we're doing. We're training a classification problem with C classes. C is a number of classes. If provided, the optional argument weight should be a 1D tensor assigning a weight to each of the classes. So we don't have to apply a weight here, but why would you apply a weight? Well, it says, if we look at weight here, this is particularly useful when you have an unbalanced training set. So just keep this in mind as you're going forward. If you wanted to train a data set that has imbalanced samples, in our case, we have the same number of samples for each class, but sometimes you might come across a data set with maybe you only have 10 yellow dots, and maybe you have 500 blue dots and only 100 red and 100 light blue dots. So you have an imbalanced data set. So that's where you can come in and have a look at the weight parameter here. But for now, we're just going to keep things simple. We have a balanced data set, and we're going to focus on using this loss function. If you'd like to read more, please, you can read on here. And if you wanted to find out more, you could go, what is cross-entropy loss? And I'm sure you'll find a whole bunch of loss functions. There we go. There's the ML cheat sheet. I love that. The ML glossary. That's one of my favorite websites. Towards data science, you'll find that website. Wikipedia. Machine Learning Mastery is also another fantastic website. But you can do that all in your own time. Let's code together, hey? We'll set up a loss function. Oh, and one more resource before we get into code is that we've got the architecture, well, the typical architecture of a classification model. The loss function for multi-class classification is cross-entropy, or torch.nn.cross-entropy loss. Let's code it out. If in doubt, code it out. So create a loss function for multi-class classification. And then we go loss fn equals nn.cross-entropy loss. Beautiful. And then we want to create an optimizer. Create an optimizer for multi-class classification. And now the beautiful thing about optimizers is they're quite flexible. They can go across a wide range of different problems. So the optimizer, so two of the most common, and I say most common because they work quite well across a wide range of problems. So that's why I've only listed two here. But of course, within the torch.optim module, you will find a lot more different optimizers. But let's stick with SGD for now. And we'll go back. We'll go optimizer equals torch.optim for optimizer, SGD for stochastic gradient descent. The parameters we want our optimizer to optimize. Model 4. We're up to our fourth model already. Oh my goodness. Model 4.parameters. And we'll set the learning rate to 0.1. Of course, you could change the learning rate if you wanted to. In fact, I'd encourage you to see what happens if you do. Because why? The learning rate is a hyperparameter. I'm better at writing code than I am at spelling. You can change. Wonderful. So we've now got a loss function and an optimizer for a multi-class classification problem. What's next? Well, we could start to building a training loop. We could start to do that, but I think we have a look at what the outputs of our model are. So more specifically, so getting prediction probabilities for a multi-class PyTorch model. So my challenge to you before the next video is to have a look at what happens if you pass XBlob test through a model. And remember, what is a model's raw outputs? What is that referred to as? Oh, I'll let you have a think about that before the next video. I'll see you there. Welcome back. In the last video, we created a loss function and an optimizer for our multi-class classification model. And recall, the loss function measures how wrong our model's predictions are. And the optimizer updates our model parameters to try and reduce the loss. So that's what that does. And I also issued the challenge of doing a forward pass with model 4, which is the most recent model that we created. And oh, did I just give you some code that wouldn't work? Did I do that on purpose? Maybe, maybe not. You'll never know. So if this did work, what are the raw outputs of our model? Let's get some raw outputs of our model. And if you recall, the raw outputs of a model are called logits. So we got a runtime error. Expected all tensors to be on the same device. Oh, of course. Why did this come up? Well, because if we go next, model 4 dot parameters, and if we check device, what happens here? Oh, we need to bring this in. Our model is on the CUDA device, whereas our data is on the CPU still. Can we go X? Is our data a tensor? Can we check the device parameter of that? I think we can. I might be proven wrong here. Oh, it's on the CPU. Of course we're getting a runtime error. Did you catch that one? If you did, well done. So let's see what happens. But before we do a forward pass, how about we turn our model into a val mode to make some predictions with torch.inference mode. We'll make some predictions. We don't necessarily have to do this because it's just tests, but it's a good habit. Oh, y preds equals, what do we get? Y preds, and maybe we'll just view the first 10. What do we get here? Oh my goodness, a whole bunch of numbers on a page. Is this the same format as our data or our test labels? Let's have a look. No, it's not. Okay. Oh, we need Y blob test. Excuse me. I'm going to make that mistake a fair few times here. So we need to get this into the format of this. How can we do that? Now, I want you to notice one thing as well, is that we have one value here per one value, except that this is actually 4 values. Now, why is that? We have 1, 2, 3, 4. Well, that is because we set the out features up here. Our model outputs 4 features per sample. So each sample right now has 4 numbers associated with it. And what are these called? These are the logits. Now, what we have to do here, so let's just write this down. In order to evaluate and train and test our model, we need to convert our model's outputs which are logits, to prediction probabilities, and then to prediction labels. So we've done this before, but for binary classification. So we have to go from logits to pred probs to pred labels. All right, I think we can do this. So we've got some logits here. Now, how do we convert these logits to prediction probabilities? Well, we use an activation function. And if we go back to our architecture, what's our output activation here? For a binary classification, we use sigmoid. But for multi-class classification, this is the 2 main differences between multi-class classification and binary classification. One uses softmax, one uses cross entropy. And it's going to take a little bit of practice to know this off by heart. It took me a while, but that's why we have nice tables like this, and that's why we write a lot of code together. So we're going to use the softmax function here to convert our logits, our model's raw outputs, which is this here, to prediction probabilities. And let's see that. So convert our model's logit outputs to prediction probabilities. So let's create Y pred probs. So I like to call prediction probabilities pred probs for short. So torch.softmax, and then we go Y logits, and we want it across the first dimension. So let's have a look. If we print Y logits, we'll get the first 5 values there. And then look at the conversion here. Y logits, or Y pred probs. That's what we want to compare. Pred probs 5. Let's check this out. Oh, what did we get wrong here? Y logits. Do we have Y logits? Oh no. We should change this to Y logits because really that's the raw output of our model here. Y logits, let's rerun that. Check that. We know that these are different to these, but we ideally want these to be in the same format as these, our test labels. These are our model's predictions. And now we should be able to convert. There we go. Okay, beautiful. What's happening here? Let's just get out of this. And we will add a few code cells here so we have some space. Now, if you wanted to find out what's happening with torch.softmax, what could you do? We could go torch softmax, see what's happening. Softmax. Okay, so here's the function that's happening. We replicated some nonlinear activation functions before. So if you wanted to replicate this, what could you do? Well, if in doubt, code it out. You could code this out. You've got the tools to do so. We've got softmax to some x input, takes the exponential of x, so torch exponential over the sum of torch exponential of x. So I think you could code that out if you wanted to, but let's for now just stick with what we've got. We've got some logits here, and we've got some softmax, some logits that have been passed through the softmax function. So that's what's happened here. We've passed our logits as the input here, and it's gone through this activation function. These are prediction probabilities. And you might be like, Daniel, these are still just numbers on a page. But you'll also notice that none of them are negative. Okay, and there's another little tidbit about what's going on here. If we sum one of them up, let's get the first one. Will this work? And if we go torch.sum, what happens? Oh, they all sum up to 1. So that's one of the effects of the softmax function. And then if we go torch.max of ypredprobs, so this is a prediction probability. For multi-class, you'll find that for this particular sample here, the 0th sample, this is the maximum number. And so our model, what this is saying is our model is saying, this is the prediction probability, this is how much I think it is class 0. This number here, it's in order. This is how much I think it is class 1. This is how much I think it is class 2. This is how much I think it is class 3. And so we have one value for each of our 4 classes. A little bit confusing because it's 0th indexed. But the maximum value here is this index. And so how would we get the particular index value of whatever the maximum number is across these values? Well, we can take the argmax, and we get tensor 1. So for this particular sample, this one here, our model and these guesses or these predictions aren't very good. Why is that? Well, because our model is still just predicting with random numbers. We haven't trained it yet. So this is just random output here, basically. But for now, the premise still remains that our model thinks that for this sample, using random numbers, it thinks that index 1 is the right class, or class number 1. For this particular sample. And then for this next one, what's the maximum number here? I think it would be the 0th index. And the same for the next one. What's the maximum number here? Well, it would be the 0th index as well. But of course, these numbers are going to change once we've trained our model. So how do we get the maximum index value of all of these? So this is where we can go convert our model's prediction probabilities to prediction labels. So let's do that. We can go ypreds equals torch.argmax on ypredprobs, and if we go across the first dimension as well. So now let's have a look at ypreds. Do we have prediction labels in the same format as our yblob test? Beautiful, yes we do. Although many of them are wrong, as you can see. Ideally they would line up with each other, but because our model is predicting or making predictions with random numbers, so our model hasn't been trained, all of these are basically random outputs. So hopefully once we train our model, it's going to line up, the values of the predictions are going to line up with the values of the test labels. But that is how we go from our model's raw outputs to prediction probabilities, to prediction labels for a multi-class classification problem. So let's just add the steps here, logits, raw output of the model, pred probs. To get the prediction probabilities, use torch.softmax or the softmax activation function. Pred labels, take the argmax of the prediction probabilities. So we're going to see this in action later on when we evaluate our model, but I feel like now that we know how to go from logits to prediction probabilities to pred labels, we can write a training loop. So let's set that up. 8.5, create a training loop and testing loop for a multi-class PyTorch model. This is so exciting. I'll see you in the next video. Let's build our first training and testing loop for a multi-class PyTorch model. And I'll give you a little hint. It's quite similar to the training and testing loops we've built before, so you might want to give it a shot. I think you can. Otherwise, we'll do it together in the next video. Welcome back. In the last video, we covered how to go from raw logits, which is the output of the model, the raw output of the model for a multi-class PyTorch model. Then we turned our logits into prediction probabilities using torch.softmax. And then we turn those prediction probabilities into prediction labels by taking the argmax, which returns the index of where the maximum value occurs in the prediction probability. So for this particular sample, with these 4 values, because it outputs 4 values, because we're working with 4 classes, if we were working with 10 classes, it would have 10 values. The principle of these steps would still be the same. So for this particular sample, this is the value that's the maximum. So we would take that index, which is 1. For this one, the index 0 has the maximum value. For this sample, same again, and then same again. I mean, these prediction labels are just random, right? So they're quite terrible. But now we're going to change that because we're going to build a training and testing loop for our multi-class model. Let's do that. So fit the multi-class model to the data. Let's go set up some manual seeds. Torch.manual seed. Again, don't worry too much if our numbers on the page are not exactly the same. That's inherent to the randomness of machine learning. We're setting up the manual seeds to try and get them as close as possible, but these do not guarantee complete determinism, which means the same output, but we're going to try. The direction is more important. Set number of epochs. We're going to go epochs. How about we just do 100? I reckon we'll start with that. We can bump it up to 1,000 if we really wanted to. Let's put the data to the target device. What's our target device? Well, it doesn't really matter because we've set device agnostic code. So whether we're working with a CPU or a GPU, our code will use whatever device is available. I'm typing blog again. So we've got X blob train, Y blob train. This is going to go where? It's going to go to the device. And Y blob train to device. And we're going to go X blob test. And then Y blob test equals X blob test to device. Otherwise, we'll get device issues later on. And we'll send this to device as well. Beautiful. Now what do we do now? Well, we loop through data. Loop through data. So for an epoch in range epochs, for an epoch in a range epochs. I don't want that autocorrect. Come on, Google Colab, work with me here. We're training our first multi-class classification model. This is serious business. No, I'm joking. It's actually quite fun. So model4.train. And let's do the forward pass. I'm not going to put much commentary here because we've been through this before, but what are the logits? The logits are raw outputs of our model. So we'll just go X blob train and X test. I didn't want that. X blob train. Why did that do that? I need to turn off autocorrect in Google Colab. I've been saying it for a long time. Ypred equals torch.softmax. So what are we doing here? We're going from logits to prediction probabilities here. So torch softmax y logits across the first dimension. And then we can take the argmax of this and dim equals 1. In fact, I'm going to show you a little bit of, I've written blog here. Maybe autocorrect would have been helpful for that. A little trick, you don't actually have to do the torch softmax. The logits, if you just took the argmax of the logits, here's a little test for you. Just take the argmax of the logits and see, do you get the same similar outputs as what you get here? So I've seen that done before, but for completeness, we're going to use the softmax activation function because you'll often see this in practice. And now what do? We calculate the loss. So the loss Fn, where you're going to use categorical cross entropy here, or just cross entropy loss. So if we check our loss function, what do we have? We have cross entropy loss. We're going to compare our model's logits to y blob train. And then what are we going to do? We're going to calculate the accuracy because we're working with a classification problem. It'd be nice if we had accuracy as well as loss. Accuracy is one of the main classification evaluation metrics. Ypred equals ypred. Ypred. And now what do? Well, we have to zero grad the optimizer. Optimizer zero grad. Then we go loss backward. And then we step the optimizer. Optimizer step, step, step. So none of these steps we haven't covered before. We do the forward pass, we calculate the loss and any evaluation metric we choose to do so. We zero the optimizer, we perform backpropagation on the loss, and we step the optimizer. The optimizer will hopefully behind the scenes update the parameters of our model to better represent the patterns in our training data. And so we're going to go testing code here. What do we do for testing code? Well, or inference code. We set our model to eval mode. That's going to turn off a few things behind the scenes that our model doesn't need, such as dropout layers, which we haven't covered, but you're more than welcome to check them out if you go torch nn. Dropout layers, do we have dropout? Dropout layers, beautiful. And another one that it turns off is batch norm. Beautiful. And also you could search this. What does model.eval do? And you might come across Stack Overflow question, one of my favorite resources. So there's a little bit of extra curriculum, but I prefer to see things in action. So with torch inference mode, again, this turns off things like gradient tracking and a few more things. So we get as fast as code as possible because we don't need to track gradients when we're making predictions. We just need to use the parameters that our model has learned. We want xblob test to go to our model here for the test logits, and then for the test preds, we're going to do the same step as what we've done here. We're going to go torch.softmax on the test logits across the first dimension, and we're going to call the argmax on that to get the index value of where the maximum prediction probability value occurs. We're going to calculate the test loss or loss function. We're going to pass in what? The test logits here. Then we're going to pass in y blob test, compare the test logits. Behind the scenes, our loss function is going to do some things that convert the test logits into the same format as our test labels and then return us a value for that. Then we'll also calculate the test accuracy here by passing in the y true as y blob test. And we have the ypred equals ypred. Wonderful. And then what's our final step? Well, we want to print out what's happening because I love seeing metrics as our model trains. It's one of my favorite things to watch. If we go if epoch, let's do it every 10 epochs because we've got 100 so far, equals 0. Let's print out a nice F string with epoch. And then we're going to go loss. What do we put in here? We'll get our loss value, but we'll take it to 4 decimal places. And we'll get the training accuracy, which will be acc. And we'll take this to 2 decimal places. And we'll get a nice percentage sign there. And we'll go test loss equals test loss. And we'll go there. And finally, we'll go test acc at the end here. Test acc. Now, I'm sure by now, we've written a fair few of these. You're either getting sick of them, or you're like, wow, I can actually do the steps through here. And so don't worry, we're going to be functionizing all of this later on, but I thought I'm going to include them as much as possible so that we can practice as much as possible together. So you ready? We're about to train our first multi-class classification model in 3, 2, 1. Let's go. No typos. Oh, of course. What did we get wrong here? Oh, this is a fun error. Runtime error. NLL loss forward reduce CUDA kernel 2D index not implemented for float. Okay, that's a pretty full-on bunch of words there. I don't really know how to describe that. But here's a little hint. We've got float there. So we know that float is what? Float is a form of data. It's a data type. So potentially, because that's our hint, we said not implemented for float, so maybe we've got something wrong up here. Our data is of the wrong type. Can you see anywhere where our data might be the wrong type? Well, let's print it out. Where's our issue? Here. Y logits, Y blob train. Okay, Y blob train and Y logits. What does Y blob train look like? Y blob train. Okay, and what's the D type here? Float, okay. So it's not implemented for float. Maybe we have to turn them into a different data type. What if we went type torch long tensor? What happens here? Expected all tensors to be on the same device, but found at least 2 devices. Oh my goodness, what have we got wrong here? Type torch long tensor. Friends, guess what? I found it. And so it was to do with this pesky little data type issue here. So if we run this again, and now this one took me a while to find, and I want you to know that behind the scenes, even though, again, this is a machine learning cooking show, it still takes a while to troubleshoot code, and you're going to come across this, but I thought rather than spend 10 minutes doing it in a video, I'll show you what I did. So we went through this and we found that, there's something going on here. I don't quite know what this is, and that seems quite like a long string of words, not implemented for float. And then we looked back at the line where it went wrong, and so that we know that maybe the float is hinting at that one of these 2 tensors is of the wrong data type. Now, why would we think that it's the wrong data type? Well, because anytime you see float or int or something like that, it generally hints at one of your data types being wrong. And so the error is actually right back up here where we created our tensor data. So we turned our labels here into floats, which generally is okay in PyTorch. However, this one should be of type torch.long tensor, which we haven't seen before, but if we go into torch long tensor, let's have a look. Torch.tensor. Do we have long tensor? Here we go. 64-bit integer signed. So why do we need torch.long tensor? And again, this took me a while to find, so I want to express this, that in your own code, you probably will butt your head up against some issues and errors that do take you a while to find, and data types is one of the main ones. But if we look in the documentation for cross-entropy loss, the way I kind of found this out was this little hint here. The performance of the criterion is generally better when the target contains class indices, as this allows for optimized computation. But I read this and it says target contains class indices. And I'm like, ours are indices already, but maybe they should be integers and not floats. But then if you actually just look at the sample code, you would find that they use dtype equals torch.long. Now, that's the thing with a lot of code around the internet, is that sometimes the answer you're looking for is a little bit buried. But if in doubt, run the code and butt your head up against a wall for a bit and keep going. So let's just rerun all of this and see, do we have an error here? Let's train our first multi-class classification model together. No errors, fingers crossed. Well, what did we get wrong here? Okay, so we've got different size. We're slowly working through all of the errors in deep learning here. Value error, input batch size 200 to match target size 200. So this is telling me maybe our test data, which is of size 200, is getting mixed up with our training data, which is of size 800. So we've got test loss, the test logits, model 4. What's the size? Let's print out print test logits.shape and y blob test. So troubleshooting on the fly here, everyone. What do we got? Torch size 800. Where are our test labels coming from? Y blob test equals, oh, there we go. Did you catch that before? Maybe you did, maybe you didn't, but I think we should be right here. Now, if we just comment out this line. So we've had a data type issue and we've had a shape issue. Two of the main in machine learning. Oh, and again, we've had some issues. Y blob test, what's going on here? I thought we just changed the shape. Oh no, we have to go up and reassign it again because now this is definitely Y blob, yes. Let's rerun all of this, reassign our data. We are running into every single error here, but I'm glad we're doing this because otherwise you might not see how to troubleshoot these type of things. So the size of a tensor must match the size. Oh, we're getting the issue here. Oh, test preds. Oh my goodness, we have written so much code here. Test pred. So instead of Y pred, this should be test preds. Fingers crossed. Are we training our first model yet or what? There we go. Okay, and we're printing out some stuff. I don't really want to print out that stuff, and I want to see the loss go down, so I'm going to... So friends, I hope you know that we've just been through some of the most fundamental troubleshooting steps, and you might say, oh, Daniel, that's a cop-out because you're just coding wrong, and in fact, I code wrong all the time. But we've now worked out how to troubleshoot them, shape errors and data type errors. But look at this! After all of that... Thank goodness, our loss and accuracy go in the directions that we want them to go. So our loss goes down and our accuracy goes up. Beautiful. So it looks like that our model is working on a multi-class classification data set. So how do we check that? Well, we're going to evaluate it in the next step by visualize, visualize, visualize. So you might want to give that a shot. See if you can use our plot decision boundary function. We'll use our model to separate the data here. So it's going to be much the same as what we did for binary classification, but this time we're using a different model and a different data set. I'll see you there. Welcome back. In the last video, we went through some of the steps that we've been through before in terms of training and testing a model, but we also butted our heads up against two of the most common issues in machine learning and deep learning in general, and that is data type issues and shape issues, but luckily we were able to resolve them, and trust me, you're going to run across many of them in your own deep learning and machine learning endeavors, so I'm glad that we got to have a look at them and sort of I could show you what I do to troubleshoot them. But in reality, it's a lot of experimentation. Run the code, see what errors come out, Google the errors, read the documentation, try again. But with that being said, it looks like that our multi-class classification model has learned something. The loss is going down, the accuracy is going up, but we can further evaluate this by making and evaluating predictions with a PyTorch multi-class model. So how do we make predictions? We've seen this step before, but let's reiterate. Make predictions. We're going to set our model to what mode? Eval mode. And then we're going to turn on what context manager? Inference mode, because we want to make inference. We want to make predictions. Now, what do we make predictions on? Or what are the predictions? They're going to be logits, because why? They are the raw outputs of our model. So we'll take model 4, which we just trained, and we'll pass it the test data. Well, it needs to be blob test, by the way. I keep getting that variable mixed up. We just had enough problems with the data, Daniel. We don't need any more. You're completely right. I agree with you. But we're probably going to come across some more problems in the future, don't you worry about that. So let's view the first 10 predictions. Y logits, what do they look like? All right, just numbers on the page. They're raw logits. Now, how do we go from logits to prediction probabilities? How do we do that? With a multi-class model, we go ypredprobs equals torch.softmax on the Y logits. And we want to do it across the first dimension. And what do we have when we go predprobs? Let's go up to the first 10. Are we apples to apples yet? What does our Y blob test look like? We're not apples to apples yet, but we're close. So these are prediction probabilities. You'll notice that we get some fairly different values here. And remember, the one closest to 1 here, the value closest to 1, which looks like it's this, the index of the maximum value is going to be our model's predicted class. So this index is index 1. And does it correlate here? Yes, 1. Beautiful. Then we have index 3, which is the maximum value here. 3. Beautiful. And then we have, what do we have here? Index 2. Yes. Okay, wonderful. But let's not step through that. We're programmers. We can do this with code. So now let's go from pred probs to pred labels. So y preds equals, how do we do that? Well, we can do torch.argmax on the y pred probs, and then we can pass dim equals 1. We could also do it this way, y pred probs call dot argmax. There's no real difference between these two, but we're just going to do it this way, call torch.argmax, y preds, let's view the first 10. Are we now comparing apples to apples when we go y blob test? Yes, we are. Have a go at that. Look, 1, 3, 2, 1, 0, 3, 1, 3, 2, 1, 0, 3. Beautiful. Now, we could line these up and look at and compare them all day. I mean, that would be fun, but I know what's something that would be even more fun. Let's get visual. So, plot.figure, and we're going to go fig size equals 12:6, just because the beauty of this being a cooking show is I kind of know what ingredients work from ahead of time, despite what you saw in the last video with all of that troubleshooting. But I'm actually glad that we did that because, seriously, shape issues and data type issues, you're going to come across a lot of them. They're two of the main issues I troubleshoot, aside from device issues. So let's go x blob train and y blob train. And we're going to do another plot here. We're going to get subplot 1, 2, 2. And we're going to do this for the test data. Test, and then plot decision boundary. Plot decision boundary with model 4 on x blob test and y blob test as well. Let's see this. Did we train a multi-class? Oh my goodness, yes we did! Our code worked faster than I can speak. Look at that beautiful looking plot. We've separated our data almost as best as what we could. Like there's some here that are quite inconspicuous. And now, what's the thing about these lines? Would this model have worked? I posed the question a fair few videos ago, whenever we created our multi-class model, that could we separate this data without nonlinear functions? So how about we just test that? Since we've got the code ready, let's go back up. We've got nonlinear functions here. We've got relu here. So I'm just going to recreate our model there. So I just took relu out. That's all I did, commented it out. This code will still all work. And, or fingers crossed it will. Don't count your chickens before they hatch, Daniel. Come on. We're just going to rerun all of these cells. All the code's going to stay the same. All we did was we took the nonlinearity out of our model. Is it still going to work? Oh my goodness, it still works. Now, why is that? Well, you'll notice that the lines are a lot more straighter here. Did we get different metrics? I'll leave that for you to compare. Maybe these will be a little bit different. I don't think they're too far different. But that is because our data is linearly separable. So we can draw straight lines only to separate our data. However, a lot of the data that you deal with in practice will require linear and nonlinear, hence why we spent a lot of time on that. Like the circle data that we covered before. And let's look up an image of a pizza. If you were building a food vision model to take photos of food and separate different classes of food, could you do this with just straight lines? Well, you might be able to, but I personally don't think that I could build a model to do such a thing. And in fact, PyTorch makes it so easy to add non-linearities to our model, we might as well have them in so that our model can use it if it needs it, and if it doesn't need it, well, hey, it's going to build a pretty good model, as we saw before, if we included the non-linearities in our model. So we could uncomment these and our model is still going to perform quite well. That is the beauty of neural networks, is that they decide the numbers that should represent our data the best. And so, with that being said, we've evaluated our model, we've trained our multi-class classification model, we've put everything together, we've gone from binary classification to multi-class classification. I think there's just one more thing that we should cover, And that is, let's go here, section number 9, a few more classification metrics. So, as I said before, evaluating a model, let's just put it here, to evaluate our model, our classification models, that is, evaluating a model is just as important as training a model. So I'll see you in the next video. Let's cover a few more classification metrics. Welcome back. In the last video, we evaluated our multi-class classification model visually, and we saw that it did pretty darn well because our data turned out to be linearly separable, so our model, even without nonlinear functions, could separate the data here. However, as I said before, most of the data that you deal with will require some form of linear and nonlinear function. So just keep that in mind, and the beauty of PyTorch is that it allows us to create models with linear and nonlinear functions quite flexibly. So let's write down here, if we wanted to further evaluate our classification models, we've seen accuracy. So accuracy is one of the main methods of evaluating classification models. So this is like saying, out of 100 samples, how many does our model get right? And so we've seen our model right now is at testing accuracy of nearly 100%, so it's nearly perfect. But of course, there were a few tough samples, which, a little bit hard. Some of them are even within the other samples, so you can forgive it a little bit here for not being exactly perfect. What are some other metrics here? Well, we've also got precision, and we've also got recall. Both of these will be pretty important when you have classes with different amounts of values in them, so precision and recall. Accuracy is pretty good to use when you have balanced classes. So this is just text on a page for now. F1 score, which combines precision and recall. There's also a confusion matrix, and there's also a classification report. So I'm going to show you a few code examples of where you can access these, and I'm going to leave it to you as extra curriculum to try each one of these out. So let's go into the keynote. And by the way, you should pat yourself on the back here because we've just gone through all of the PyTorch workflow for a classification problem. Not only just binary classification, we've done multi-class classification as well. So let's not stop there though. Remember, building a model, evaluating a model is just as important as building a model. So we've been through nonlinearity. We've seen how we could replicate nonlinear functions. We've talked about the Machine Learning Explorer's motto, visualize, visualize, visualize. Machine Learning Practitioner's motto is experiment, experiment, experiment. I think I called that the Machine Learning or Data Scientist motto. Same thing, you know? And steps in modeling with PyTorch, we've seen this in practice, so we don't need to look at these slides. They'll be available on the GitHub if you want them, but here we are. Some common classification evaluation methods. So we have accuracy. There's the formal formula if you want, but there's also code, which is what we've been focusing on. So we wrote our own accuracy function, which replicates this. By the way, TP stands for not toilet paper, it stands for true positive. TN is true negative, false positive, FP, false negative, FN. And so the code, we could do torch metrics. Oh, what's that? But when should you use it? The default metric for classification problems. Note, it is not the best for imbalanced classes. So if you had, for example, 1,000 samples of one class, so number one, label number one, but you had only 10 samples of class 0. So accuracy might not be the best to use for then. For imbalanced data sets, you might want to look into precision and recall. So there's a great article called, I think it's Beyond Accuracy, Precision and Recall, which gives a fantastic overview of, there we go, this is what I'd recommend. There we go, by Will Coeshran. So I'd highly recommend this article as some extra curriculum here. See this article for when to use precision recall. We'll go there. Now, if we look back, there is the formal formula for precision, true positive over true positive plus false positive. So higher precision leads to less false positives. So if false positives are not ideal, you probably want to increase precision. If false negatives are not ideal, you want to increase your recall metric. However, you should be aware that there is such thing as a precision recall trade-off, and you're going to find this in your experimentation. precision recall trade-off. So that means that generally if you increase precision, you lower recall. And inversely, if you increase precision, you lower recall. So check out that just to be aware of that. But again, you're going to learn this through practice of evaluating your models. If you'd like some code to do precision and recall, you've got torchmetrics.precision or torchmetrics.recall, as well as scikit-learn. So scikit-learn has implementations for many different classification metrics. Torchmetrics is a pytorch-like library. And then we have F1 score, which combines precision and recall. So it's a good combination if you want something in between these two. And then finally, there's a confusion matrix. I haven't listed here a classification report, but I've listed it up here. And we can see a classification report in scikit-learn. Classification report. Classification report kind of just puts together all of the metrics that we've talked about. And we can go there. But I've been talking a lot about torch metrics. So let's look up torch metrics accuracy. Torch metrics. So this is a library. I don't think it comes with Google Colab at the moment, but you can import torch metrics and you can initialize a metric. So we've built our own accuracy function, but the beauty of using torch metrics is that it uses PyTorch-like code. So we've got metric, preds, and target. And then we can find out what the value of the accuracy is. And if you wanted to implement your own metrics, you could subclass the metric class here. But let's just practice this. So let's check to see if I'm going to grab this and copy this in here. If you want access to a lot of PyTorch metrics, see torch metrics. So can we import torch metrics? Maybe it's already in Google Colab. No, not here, but that's all right. We'll go pip install torch metrics. So Google Colab has access to torch metrics, and that's going to download from torch metrics. It shouldn't take too long. It's quite a small package, beautiful. And now we're going to go from torch metrics, import accuracy. Wonderful. And let's see how we can use this. So setup metric. So we're going to go torch metric underscore accuracy. We could call it whatever we want really, but we need accuracy here. We're just going to set up the class, and then we're going to calculate the accuracy of our multi-class model by calling it torch metric accuracy, and we're going to pass it ypreds and yblob test. Let's see what happens here. Oh, what did we get wrong? Runtime error. Expected all tensors to be on the same device, but found at least 2 devices. Oh, of course. Now, remember how I said torch metrics implements PyTorch-like code? Well, let's check what device this is on. Oh, it's on the CPU. So, something to be aware of, that if you use torch metrics, you have to make sure your metrics are on the same device by using device-agnostic code as your data. So if we run this, what do we get? Beautiful. We get an accuracy of 99.5%, which is in line with the accuracy function that we coded ourselves. So if you'd like a lot of pre-built metrics functions, be sure to see either scikit-learn for any of these or torch metrics for any PyTorch-like metrics, but just be aware, if you use the PyTorch version, they have to be on the same device. And if you'd like to install it, what do we have? Where's the metrics? Module metrics. Do we have classification? There we go. So look how many different types of classification metrics there are from torch metrics. So I'll leave that for you to explore. The resources for this will be here. This is an extracurriculum article for when to use precision and recall. And another extracurriculum would be to go through the torch metrics module for 10 minutes and have a look at the different metrics for classification. So with that being said, I think we've covered a fair bit. But I think it's also time for you to practice what you've learned. So let's cover some exercises in the next video. I'll see you there. Welcome back. In the last video, we looked at a few more classification metrics, a little bit of a high-level overview for some more ways to evaluate your classification models. And I linked some extra curriculum here that you might want to look into as well. But we have covered a whole bunch of code together. But now it's time for you to practice some of this stuff on your own. And so I have some exercises prepared. Now, where do you go for the exercises? Well, remember, on the learnpytorch.io book, for each one of these chapters, there's a section. Now, just have a look at how much we've covered. If I scroll, just keep scrolling. Look at that. We've covered all of that in this module. That's a fair bit of stuff. But down the bottom of each one is an exercises section. So all exercises are focusing on practicing the code in the sections above, all of these sections here. We've got number 1, 2, 3, 4, 5, 6, 7. Yeah, 7 exercises, nice, writing plenty of code. And then, of course, extra curriculum. So these are some challenges that I've mentioned throughout the entire section 02. But I'm going to link this in here, exercises. But of course, you can just find it on the learnpytorch.io book. So if we come in here and we just create another heading, exercises and extra curriculum. And then we just write in here, see exercises and extra curriculum here. And so if you'd like a template of the exercise code, you can go to the PyTorch Deep Learning repo. And then within the extras folder, we have exercises and solutions. You might be able to guess what's in each of these. Exercises, we have O2 PyTorch classification exercises. This is going to be some skeleton code. And then of course we have the solutions as well. Now this is just one form of solutions, but I'm not going to look at those because I would recommend you looking at the exercises first before you go into the solutions. So we have things like import torch, set up device agnostic code, create a data set, turn data into a data frame, and then etc. for the things that we've done throughout this section. So give that a go, try it on your own, and if you get stuck, you can refer to the notebook that we've coded together, all of this code here. You can refer to the documentation, of course, and then you can refer to, as a last resort, the solutions notebooks. So give that a shot, and congratulations on finishing section 02, PyTorch classification. Now, if you're still there, you're still with me, let's move on to the next section. We're going to cover a few more things of deep learning with PyTorch. I'll see you there. Hello and welcome back. We've got another section. We've got computer vision and convolutional neural networks with PyTorch. Now, computer vision is one of my favorite deep learning topics. But before we get into the materials, let's answer a very important question, and that is, where can you get help? So, first and foremost is to follow along with the code as best you can. We're going to be writing a whole bunch of PyTorch computer vision code, and remember our motto, if in doubt, run the code. See what the inputs and outputs are of your code. And that's try it yourself. If you need the doc string to read about what the function you're using does, you can press Shift Command and Space in Google Colab, or it might be Control if you're on Windows. Otherwise, if you're still stuck, you can search for the code that you're running. You might come across Stack Overflow or the PyTorch documentation. We've spent a bunch of time in the PyTorch documentation already, and we're going to be referencing a whole bunch in the next module, in section 3 we're up to now. If you go through all of these 4 steps, the next step is to try it again. If in doubt, run the code. And then of course, if you're still stuck, you can ask a question on the PyTorch Deep Learning repo discussions tab. Now, if we open this up, we can go new discussion, and you can write here, section 03 for the computer vision. My problem is, and then in here, you can write some code. Be sure to format it as best you can. That way it'll help us answer it. And then go, what's happening here? Now, why do I format the code in these backticks here? It's so that it looks like code and that it's easier to read when it's formatted on the GitHub discussion. Then you can select a category. If you have a general chat, an idea, a poll, a Q&A, or a show and tell of something you've made for what you've learned from the course. For question and answering, you want to put it as Q&A. Then you can click Start Discussion, and it'll appear here. And that way they'll be searchable and we'll be able to help you out. So I'm going to get out of this. And speaking of resources, We've got the PyTorch Deep Learning repo. The links will be where you need the links. All of the code that we're going to write in this section is contained within the Section 3 notebook, PyTorch Computer Vision. Now, this is a beautiful notebook, annotated with heaps of text and images. You can go through this on your own time and use it as a reference to help out. If you get stuck on any of the code we write through the videos, check it out in this notebook, because it's probably here somewhere. And then finally, let's get out of these. If we come to the book version of the course, this is learnpytorch.io. We've got home. This will probably be updated by the time you look at that. But we have Section 03, which is PyTorch Computer Vision. It's got all of the information about what we're going to cover in a book format. And you can, of course, skip ahead to different subtitles, see what we're going to write here. All of the links you need and extra resources will be at learnpytorch.io. And for this section, it's PyTorch Computer Vision. With that being said, speaking of computer vision, you might have the question, what is a computer vision problem? Well, if you can see it, it could probably be phrased as some sort of computer vision problem. That's how broad computer vision is. So let's have a few concrete examples. We might have a binary classification problem, such as if we wanted to have two different images. Is this photo of steak or pizza? We might build a model that understands what steak looks like in an image. This is a beautiful dish that I cooked, by the way. This is of me eating pizza at a cafe with my dad. And so we could have binary classification, one thing or another. And so our machine learning model may take in the pixels of an image and understand the different patterns that go into what a steak looks like. And the same thing with a pizza. Now, the important thing to note is that we won't actually be telling our model what to learn. It will learn those patterns itself from different example of images. Then we could step things up and have a multi-class classification problem. You noticing a trend here? We've covered classification before, but classification can be quite broad. It can be across different domains, such as vision or text or audio. But if we were working with multi-class classification for an image problem, we might have, is this a photo of sushi, steak, or pizza? And then we have 3 classes instead of 2. But again, this could be 100 classes, such as what Nutrify uses, which is an app that I'm working on. If we go to nutrify.app, this is bare bones at the moment, but right now Nutrify can classify up to 100 different foods. So if you were to upload an image of food, let's give it a try. Nutrify, we'll go into images, and we'll go into sample food images, and how about some chicken wings? What does it classify this as? Chicken wings. Beautiful. And then if we uploaded an image of not food, maybe. Let's go to Nutrify. This is on my computer, by the way. You might not have a sample folder set up like this. And then if we upload a photo of a Cybertruck, what does it say? No food found. Please try another image. So behind the scenes, Nutrify is using the pixels of an image and then running them through a machine learning model and classifying it first whether it's food or not food. And then if it is food, classifying it as what food it is. So right now it works for 100 different foods. So if we have a look at all of these, it can classify apples, artichokes, avocados, barbecue sauce. Each of these work at different levels of performance, but that's just something to keep in mind of what you can do. So the whole premise of Nutrify is to upload a photo of food and then learn about the nutrition about it. So let's go back to our keynote. What's another example? Well, we could use computer vision for object detection, where you might answer the question is, where's the thing we're looking for? So, for example, this car here, I caught them on security camera, actually did a hit and run on my new car. It wasn't that much of an expensive car, but I parked it on the street, and this person, the trailer came off the back of their car and hit my car, and then they just picked the trailer up and drove away. But I went to my neighbor's house and had a look at their security footage, and they found this car. So potentially, you could design a machine learning model to find this certain type of car. It was an orange ute, by the way, but the images were in black and white, to detect, to see if it ever recognizes a similar car that comes across the street. And you can go, hey, did you crash into my car the other day? I didn't actually find who it was, so sadly, it was a hit and run. But that's object detection, finding something in an image. And then you might want to find out what are the different sections in this image. So this is a great example of what Apple uses on their devices, iPhones and iPads and whatnot, to segregate or segment the different sections of an image, so person 1, person 2, skin tones, hair, sky, original, and then it enhances each of these sections in different ways. So that's a practice known as computational photography. But the whole premise is, how do you segment different portions of an image? And then there's a great blog post here that talks about how it works and what it does and what kind of model that's used. I'll leave that as extra curriculum if you'd like to look into it. So if you have these images, how do you enhance the sky? How do you make the skin tones look how they should? How do you remove the background if you really wanted to? So all of this happens on device. So that's where I got that image from, by the way. Semantic Mars. And this is another great blog, Apple Machine Learning Research. So to keep this in mind, we're about to see another example for computer vision, which is Tesla computer vision. A lot of companies have websites, such as Apple Machine Learning Research, where they share a whole bunch of what they're up to in the world of machine learning. So in Tesla's case, they have 8 cameras on each of their self-driving cars that fuels their full self-driving beta software. And so they use computer vision to understand what's going on in an image and then plan what's going on. So this is 3-dimensional vector space. And what this means is they're basically taking these different viewpoints from the 8 different cameras, feeding them through some form of neural network, and turning the representation of the environment around the car into a vector, so a long string of numbers. And why would it do that? Well, because computers understand numbers far more than they understand images. So we might be able to recognize what's happening here, but for a computer to understand it, we have to turn it into vector space. And so if you want to have a look at how Tesla uses computer vision, so this is from Tesla's AI Day video. I'm not going to play it all because it's 3 hours long, but I watched it and I really enjoyed it. So there's some information there. And there's a little tidbit there. If you go to 2 hours and 1 minute and 31 seconds of the same video, have a look at what Tesla do. Well, would you look at that? Where have we seen that before? That's some device-agnostic code, but with Tesla's custom Dojo chip. So Tesla uses PyTorch. So the exact same code that we're writing, Tesla uses similar PyTorch code to, of course, they write PyTorch code to suit their problem, but nonetheless, they use PyTorch code to train their machine learning models that power their self-driving software. So how cool is that? And if you want to have a look at another example, there's plenty of different Tesla self-driving videos. So, we can just play it right here. I was going to click the link. So look, this is what happens. If we have a look in the environment, Tesla, the cameras, understand what's going on here, and then it computes it into this little graphic here on your heads-up display in the car. And it kind of understands, well, I'm getting pretty close to this car, I'm getting pretty close to that car. And then it uses this information about what's happening, this perception, to plan where it should drive next. And I believe here, it ends up going into, it has to stop. Yeah, there we go. Because we've got a stop sign. Look at that. It's perceiving the stop sign. It's got 2 people here. I just saw a car drive past across this street. So that is pretty darn cool. That's just one example of computer vision, one of many. And how would you find out what computer vision can be used for? Here's what I do. What can computer vision be used for? Plenty more resources. So, there we go. 27 most popular computer vision applications in 2022. So we've covered a fair bit there. But what are we going to cover specifically with PyTorch code? Well, broadly. My bad. We're going to get a vision data set to work with using Torch Vision. So PyTorch has a lot of different domain libraries. Torch Vision helps us deal with computer vision problems. And there's existing data sets that we can leverage to play around with computer vision. We're going to have a look at the architecture of a convolutional neural network, also known as a CNN with PyTorch. We're going to look at an end-to-end multi-class image classification problem. So multi-class is what? More than one thing or another. Could be 3 classes, could be 100. We're going to look at steps at modeling with CNNs in PyTorch. So we're going to create a convolutional neural network with PyTorch. We're going to pick a loss function and optimize it to suit our problem. We're going to train a model, training a model, a little bit of a typo there. And then we're going to evaluate a model, right? So we might have typos with our text, but we'll have less typos in the code. And how are we going to do this? Well, we could do it cooks or we could do it chemists. Well, we're going to do it a little bit of both, part art, part science, but since this is a machine learning cooking show, we're going to be cooking up lots of code. So in the next video, we're going to cover the inputs and outputs of a computer vision problem. I'll see you there. So in the last video, we covered what we're going to cover broadly, and we saw some examples of what computer vision problems are. Essentially, anything that you're able to see, you can potentially turn into a computer vision problem. And we're going to be cooking up lots of machine learning, or specifically PyTorch, computer vision code. You see I fixed that typo. Now let's talk about what the inputs and outputs are of a typical computer vision problem. So let's start with a multi-classification example and say we wanted to take photos of different images of food and recognize what they were. So we're replicating the functionality of Nutrify. So take a photo of food and learn about it. So we might start with a bunch of food images that have a height and width of some sort. So we have width equals 224, height equals 224, and then they have 3 color channels. Why 3? Well, that's because we have a value for red, green, and blue. So if we look at this up, if we go red, green, blue image format, so 24-bit RGB images. So a lot of images or digital images have some value for a red pixel, a green pixel, and a blue pixel. And if you were to convert images into numbers, they get represented by some value of red, some value of green, and some value of blue. That is exactly the same as how we'd represent these images. So for example, this pixel here might be a little bit more red, a little less blue, and a little less green because it's close to orange. And then we convert that into numbers. So what we're trying to do here is essentially what we're trying to do with all of the data that we have with machine learning is represent it as numbers. So the typical image format to represent an image, because we're using computer vision, so we're trying to figure out what's in an image. The typical way to represent that is in a tensor that has a value for the height, width, and color channels. And so we might numerically encode these, in other words, represent our images as a tensor, and this would be the inputs to our machine learning algorithm. And in many cases, depending on what problem you're working on, an existing algorithm already exists for many of the most popular computer vision problems. And if it doesn't, you can build one. And then you might fashion this machine learning algorithm to output the exact shapes that you want. In our case, we want 3 outputs. We want 1 output for each class that we have. We want a prediction probability for sushi. We want a prediction probability for steak. And we want a prediction probability for pizza. Now, in our case, in this iteration, looks like our model got one of them wrong because the highest value was assigned to the wrong class here. So for the second image, it assigned a prediction probability of 0.81 for sushi. Now, keep in mind that you could change these classes to whatever your particular problem is. I'm just simplifying this and making it 3. You could have 100, you could have 1,000, you could have 5. It depends on what you're working with. And so we might use these predicted outputs to enhance our app. So if someone was to take a photo of their plate of sushi, our app might say, hey, this is a photo of sushi. Here's some information about the sushi rolls. Or the same for steak, the same for pizza. Now, it might not always get it right, because after all, that's what machine learning is. It's probabilistic. So how would we improve these results here? Well, we could show our model more and more images of sushi, steak, and pizza so that it builds up a better internal representation of said images. So when it looks at images it's never seen before or images outside its training data set, it's able to get better results. But just keep in mind this whole process is similar no matter what computer vision problem you're working with. You need a way to numerically encode your information. You need a machine learning model that's capable of fitting the data in the way that you would like it to be fit. In our case, classification. You might have a different type of model if you're working with object detection, a different type of model if you're working with segmentation. And then you need to fashion the outputs in a way that best suit your problem as well. So let's push forward. Oh, by the way, the model that often does this is a convolutional neural network. In other words, a CNN. However, you can use many other different types of machine learning algorithms here. It's just that convolutional neural networks typically perform the best with image data. Although, with recent research, there is the transformer architecture or deep learning model that also performs fairly well or very well with image data. So just keep that in mind going forward. But for now, we're going to focus on convolutional neural networks. And so we might have input and output shapes, because remember, one of the chief machine learning problems is making sure that your tensor shapes line up with each other, the input and output shapes. So if we encoded this image of steak here, we might have a dimensionality of batch size, width, height, color channels. And now the ordering here could be improved. It's usually height, then width, so alphabetical order, and then color channels last. So we might have the shape of none, 224, 2243. Now, where does this come from? So none could be the batch size. Now it's none because we can set the batch size to whatever we want, say for example 32. Then we might have a height of 224 and a width of 224 and 3 color channels. Now height and width are also customizable. You might change this to be 512 by 512. What that would mean is that you have more numbers representing your image, and in sense would take more computation to figure out the patterns because there is simply more information encoded in your image. But 224 is a common starting point for images. And then 32 is also a very common batch size, as we've seen in previous videos. But again, this could be changed depending on the hardware you're using, depending on the model you're using. You might have a batch size of 64. You might have a batch size of 512. It's all problem specific. And that's this line here. These will vary depending on the problem you're working on. So in our case, our output shape is 3 because we have 3 different classes for now. But again, if you have 100, you might have an output shape of 100. If you have 1,000, you might have an output shape of 1,000. The same premise of this whole pattern remains though. Numerically encode your data, feed it into a model, and then make sure the output shape fits your specific problem. And so, for this section, computer vision with PyTorch, we're going to be building CNNs to do this part. We're actually going to do all of the parts here, but we're going to focus on building a convolutional neural network to try and find patterns in data, because it's not always guaranteed that it will. Finally, let's look at one more problem. Say you had grayscale images of fashion items, and you have quite small images, they're only 28 by 28. The exact same pattern is going to happen. You numerically represent it, use it as inputs to a machine learning algorithm, and then hopefully your machine learning algorithm outputs the right type of clothing that it is. In this case, it's a t-shirt. But I've got ... here because we're going to be working on a problem that uses 10 different types of items of clothing. And the images are grayscale, so there's not much detail. So hopefully our machine learning algorithm can recognize what's going on in these images. There might be a boot, there might be a shirt, there might be pants, there might be a dress, etc., etc. But we numerically encode our images into dimensionality of batch size, height, width, color channels. This is known as NHWC, or number of batches or number of images in a batch, height, width, C, or color channels. This is color channels last. Why am I showing you 2 forms of this? Do you notice color channels in this one is color channels first? So color channels height, width. Well, because you come across a lot of different representations of data full stop, but particularly image data in PyTorch and other libraries, many libraries expect color channels last. However, PyTorch currently, at the time of recording this video, it may change in the future, defaults to representing image data with color channels first. Now this is very important because you will get errors if your dimensionality is in the wrong order. And so there are ways to go in between these two, and there's a lot of debate of which format is the best. It looks like color channels last is going to win over the long term, just because it's more efficient, but again, that's outside the scope. But just keep this in mind. We're going to write code to interact between these two, but it's the same data, just represented in different order. And so we could rearrange these shapes to how we want, color channels last or color channels first. And once again, the shapes will vary depending on the problem that you're working on. So with that being said, we've covered the input and output shapes. How are we going to see them with code? Well, of course, we're going to be following the PyTorch workflow that we've done. So we need to get our data ready, turn it into tensors in some way, shape, or form. We can do that with torch division transforms. Oh, we haven't seen that one yet, but we will. We can use torch utils data.dataset, utils.data.dataloader. We can then build a model or pick a pre-trained model to suit our problem. We've got a whole bunch of modules to help us with that. TorchNN module, torchvision.models. And then we have an optimizer and a loss function. We can evaluate the model using torch metrics, or we can code our own metric functions. We can, of course, improve through experimentation, which we will see later on, which we've done that, right? We've done improvement through experimentation. We've tried different models, we've tried different things. And then finally, we can save and reload our trained model if we wanted to use it elsewhere. So with that being said, we've covered the workflow. This is just a high-level overview of what we're going to code. You might be asking the question, what is a convolutional neural network, or a CNN? Let's answer that in the next video. I'll see you there. Welcome back. In the last video, we saw examples of computer vision input and output shapes. And we kind of hinted at the fact that convolutional neural networks are deep learning models, or CNNs, that are quite good at recognizing patterns in images. So we left off the last video with the question, what is a convolutional neural network? And where could you find out about that? What is a convolutional neural network? Here's one way to find out. And I'm sure, as you've seen, there's a lot of resources for such things. A comprehensive guide to convolutional neural networks. Which one of these is the best? Well, it doesn't really matter. The best one is the one that you understand the best. So there we go. There's a great video from Code Basics. I've seen that one before. Simple explanation of convolutional neural network. I'll leave you to research these things on your own. And if you wanted to look at images, there's a whole bunch of images. I prefer to learn things by writing code because remember, this course is code first. As a machine learning engineer, 99% of my time is spent writing code. So that's what we're going to focus on. But anyway, here's the typical architecture of a CNN. In other words, a convolutional neural network. If you hear me say CNN, I'm not talking about the news website. In this course, I'm talking about the architecture convolutional neural network. So this is some PyTorch code that we're going to be working towards building. But we have some hyperparameters / layer types here. We have an input layer. So we have an input layer, which takes some in channels, and an input shape, because remember, it's very important in machine learning and deep learning to line up your input and output shapes of whatever model you're using, whatever problem you're working with. Then we have some sort of convolutional layer. Now, what might happen in a convolutional layer? Well, as you might have guessed, as what happens in many neural networks, is that the layers perform some sort of mathematical operation. Now, convolutional layers perform convolving window operation across an image or across a tensor and discover patterns using, let's have a look actually. Let's go nn.conv2d. There we go. This is what happens. So the output of our network equals a bias plus the sum of the weight tensor over the convolutional channel out, okay, times input. Now, if you want to dig deeper into what is actually going on here, you're more than welcome to do that. But we're going to be writing code that leverages the torch nn-conv2d, and we're going to fix up all of these hyperparameters here so that it works with our problem. Now, what you need to know here is that this is a bias term. We've seen this before, and this is a weight matrix. So bias vector typically and a weight matrix, and they operate over the inputs. But we'll see these later on with code. So just keep that in mind. This is what's happening. As with every layer in a neural network, some form of operation is happening on our input data. And those operations happen layer by layer until eventually, hopefully, they can be turned into some usable output. So let's jump back in here. Then we have a hidden activation / nonlinear activation, because why do we use nonlinear activations? Well, it's because if our data was nonlinear, non-straight lines, we need the help of straight and non-straight lines to model it, to draw patterns in it. Then we typically have a pooling layer. And I want you to take this architecture, I've said typical here for a reason, because these type of architectures are changing all the time. So this is just one typical example of a CNN. It's about as basic as a CNN as you can get. So over time, you will start to learn to build more complex models. You will not only start to learn to build them, you will just start to learn to use them, as we'll see later on in the transfer learning section of the course. And then we have an output layer. So do you notice the trend here? We have an input layer, and then we have multiple hidden layers that perform some sort of mathematical operation on our data. And then we have an output / linear layer that converts our output into the ideal shape that we'd like. So we have an output shape here. And then how does this look in process? Well, we put in some images. They go through all of these layers here because we've used nn.sequential. And then hopefully this forward method returns x in a usable status or usable state that we can convert into class names. And then we could integrate this into our computer vision app in some way, shape, or form. And here's the asterisk here. Note, there are almost an unlimited amount of ways you could stack together a convolutional neural network. This slide only demonstrates one. So just keep that in mind. It only demonstrates one. But the best way to practice this sort of stuff is not to stare at a page. It's to, if in doubt, code it out. So let's code. I'll see you in Google Colab. Welcome back. Now, we've discussed a bunch of fundamentals about computer vision problems and convolutional neural networks, but rather than talk to more slides, let's start to code them out. I'm going to meet you at colab.research.google.com. Just going to clean up some of these tabs. And I'm going to start a new notebook. And then I'm going to name this one. This is going to be 03 PyTorch Computer Vision. And I'm going to call mine video. So just so it has the video tag. Because if we go in here, if we go video notebooks of the PyTorch Deep Learning repo, the video notebooks are stored in here. They've got the underscore video tag. So the video notebooks have all of the code I write exactly in the video, but there are some reference notebooks to go along with it. So let me just write a heading here, PyTorch Computer Vision, and I'll put a resource here, see reference notebook. Now, of course, this is the one that's the ground truth. It's got all of the code that we're going to be writing. I'm going to put that in here, explained with text and images and whatnot. And then finally is we've got C reference online book, and that is at learnpytorch.io at section number 3, PyTorch Computer Vision. I'm going to put that in there, and then I'm going to turn this into Markdown with Command MM. Beautiful. So let's get started. I'm going to get rid of this, get rid of this. How do we start this off? Well, I believe there are some computer vision libraries that you should be aware of. Computer vision libraries in PyTorch. So this is just going to be a text-based cell, but the first one is Torch Vision, which is the base domain library for PyTorch computer vision. So if we look up Torch Vision, what do we find? We have Torch Vision 0.12. That's the version that Torch Vision is currently up to at the time of recording this. So in here, this is very important to get familiar with if you're working on computer vision problems. And of course, in the documentation, this is just another tidbit. We have Torch Audio for audio problems. We have Torch Text for text. Torch Vision, which is what we're working on. Torch Rec for recommendation systems. Torch Data for dealing with different data pipelines. Torch Serve, which is for serving PyTorch models. And PyTorch on XLA, so I believe that stands for Accelerated Linear Algebra Devices. You don't have to worry about these ones for now. We're focused on Torch Vision. However, if you would like to learn more about a particular domain, this is where you would go to learn more. So there's a bunch of different stuff that's going on here. Transforming and augmenting images. So fundamentally, computer vision is dealing with things in the form of images. Even a video gets converted to an image. We have models and pre-trained weights. So as I referenced before, you can use an existing model that works on an existing computer vision problem for your own problem. We're going to cover that in section, I think it's 6 for transfer learning. And then we have data sets, which is a bunch of computer vision data sets, utils, operators, a whole bunch of stuff here. So PyTorch is really, really good for computer vision. I mean, look at all the stuff that's going on here. But that's enough talking about it. Let's just put it in here. Torch Vision, this is the main one. I'm not going to link to all of these. All of the links for these, by the way, is in the book version of the course, PyTorch Computer Vision. And we have what we're going to cover. Finally, computer vision libraries in PyTorch. Torch Vision, datasets, models, transforms, etc. But let's just write down the other ones. So we have Torch Vision datasets, something to be aware of. So get datasets and data loading functions for computer vision here. Then we have Torch Vision. So these all come from Torch Vision. Models is get pre-trained computer vision. So when I say pre-trained computer vision models, we're going to cover this more in transfer learning, as I said. Pre-trained computer vision models are models that have been already trained on some existing vision data and have trained weights, trained patterns that you can leverage for your own problems. Then we have Torch Vision transforms. And then we have functions for manipulating your vision data, which is, of course, images, to be suitable for use with an ML model. So remember, what do we have to do when we have image data or almost any kind of data? For machine learning, we have to prepare it in a way, so it can't just be pure images. So that's what transforms help us out with. Transforms helps to turn our image data into numbers so we can use it with a machine learning model. And then of course we have these are the Torch utils. This is not vision specific, it's entirety of PyTorch specific, and that's data set. So if we wanted to create our own data set with our own custom data, we have the base data set class for PyTorch. And then we have finally Torch utils data. These are just good to be aware of because you'll almost always use some form of data set / data loader with whatever PyTorch problem you're working on. So this creates a Python iterable over a data set. Wonderful. I think these are most of the libraries that we're going to be using in this section. Let's import some of them, hey, so we can see what's going on. Let's go import PyTorch. Import PyTorch. So import torch. We're also going to get NN, which stands for neural network. What's in NN? Well, in NN, of course, we have lots of layers, lots of loss functions, a whole bunch of different stuff for building neural networks. We're going to also import Torch Vision. And then we're going to go from Torch Vision, import datasets, because we're going to be using datasets later on to get a dataset to work with. From Torch Vision, we'll import transforms. You could also go from Torch Vision .transforms import toTensor. This is one of the main ones you'll see for computer vision problems, toTensor. You can imagine what it does, but let's have a look. Transforms toTensor. Transforming and augmenting images. So look where we are. We're in pytorch.org/vision/stable/transforms over here. So we're in the Torch Vision section, and we're just looking at transforming and augmenting images. So transforming, what do we have? Transforms are common image transformations available in the transforms module. They can be trained together using compose. Beautiful. So if we have toTensor, what does this do? Convert a pill image or NumPy ND array to a tensor. Beautiful. That's what we want to do later on, isn't it? Well, this is kind of me giving you a spoiler, is we want to convert our images into tensors so that we can use those with our models. But there's a whole bunch of different transforms here, and actually one of your extracurriculum is to read through each of these packages for 10 minutes. So that's about an hour of reading, but it will definitely help you later on if you get familiar with using the PyTorch documentation. After all, this course is just a momentum builder. We're going to write heaps of PyTorch code, but fundamentally, you'll be teaching yourself a lot of stuff by reading the documentation. Let's keep going with this. Where were we up to? When we're getting familiar with our data, matplotlib is going to be fundamental for visualization. Remember, the Data Explorer's motto, visualize, visualize, visualize. Become one with the data. So we're going to import matplotlib.pyplot as PLT. And then finally, let's check the versions. So print torch.version or __ version and print torch vision. So by the time you watch this, there might be a newer version of each of these modules out. If there's any errors in the code, please let me know. But this is just a bare minimum version that you'll need to complete this section. I believe at the moment, Google Colab is running 1.11 for Torch, and maybe 1.10. We'll find out in a second. It just connected. So we're importing PyTorch. Okay, there we go. So my PyTorch version is 1.10, and it's got CUDA available, and Torch Vision is 0.11. So just make sure if you're running in Google Colab, if you're running this at a later date, you'll probably have at minimum these versions. You might even have a later version. So these are the minimum versions required for this upcoming section. So we've covered the base computer vision libraries in PyTorch. We've got them ready to go. How about in the next video, we cover getting a data set. I'll see you there. Welcome back. So in the last video, we covered some of the fundamental computer vision libraries in PyTorch. The main one being Torch Vision, and then modules that stem off Torch Vision. And then of course, we've got torch utils.data.dataset, which is the base dataset class for PyTorch, and data loader, which creates a Python iterable over a dataset. So let's begin where most machine learning projects do, and that is getting a dataset. Getting a dataset. I'm going to turn this into Markdown. And the dataset that we're going to be used to demonstrating some computer vision techniques is fashion MNIST. which is a take of the data set we'll be using is Fashion MNIST, which is a take on the original MNIST dataset, MNIST database, which is Modified National Institute of Standards and Technology database, which is kind of like the hello world in machine learning and computer vision, which is, these are the sample images from the MNIST test dataset, which are grayscale images of handwritten digits. So this, I believe, was originally used for trying to find out if you could use computer vision at a postal service to, I guess, recognize postcodes and whatnot. I may be wrong about that, but that's what I know. Yeah, 1998. So all the way back at 1998. How cool is that? So this was basically where convolutional neural networks were founded. I'll let you read up on the history of that. But neural networks started to get so good that this data set was quite easy for them to do really well. And that's when Fashion MNIST came out. So this is a little bit harder. If we go into here, this is by Zalando Research, Fashion MNIST. And it's of grayscale images of pieces of clothing. So like we saw before, the input and output, what we're going to be trying to do is turning these images of clothing into numbers and then training a computer vision model to recognize what the different styles of clothing are. And here's a dimensionality plot of all the different items of clothing, visualizing where similar items are grouped together. There's the shoes and whatnot. Is this interactive? Oh no, it's a video. Excuse me. There we go. To serious machine learning researchers. We are talking about replacing MNIST. MNIST is too easy. MNIST is overused. MNIST cannot represent modern CV tasks. So even now, Fashion MNIST, I would say, has also been pretty much solved, but it's a good way to get started. Now, where could we find such a data set? We could download it from GitHub, but if we come back to the Torch Vision documentation, have a look at data sets, we have a whole bunch of built-in data sets. And remember, this is your extracurricular to read through these for 10 minutes or so each. But we have an example. We could download ImageNet if we want. We also have some base classes here for custom data sets. We'll see that later on. But if we scroll through, we have image classification data sets, Caltech 101. I don't even know what all of these are. There's a lot here. CFAR 100. So that's an example of 100 different items. So that would be a 100 class, multi-class classification problem. CFAR 10 is 10 classes. We have eMNIST. We have Fashion MNIST. Oh, that's the one we're after. But this is basically what you would do to download a data set from torchvision.datasets. You would download the data in some way, shape, or form, and then you would turn it into a data loader. So ImageNet is one of the most popular, or is probably the gold standard data set for computer vision evaluation. It's quite a big data set. It's got millions of images, but that's the beauty of Torch Vision, is that it allows us to download example data sets that we can practice on, or even perform research on from a built-in module. So let's now have a look at the Fashion MNIST data set. How might we get this? So we've got some example code here, or this is the documentation, torchvision.datasets.fashionmnist. We have to pass in a route, so where do we want to download the data set? We also have to pass in whether we want the training version of the data set or whether we want the testing version of the data set. Do we want to download it? Yes or no? Should we transform the data in any way, shape, or form? So when we're going to be downloading images through this function call or this class call, do we want to transform those images in some way? What do we have to do to images before we can use them with a model? We have to turn them into a tensor, so we might look into that in a moment. And target transform is, do we want to transform the labels in any way, shape, or form? So often the datasets that you download from torchvision.datasets are pre-formatted in a way that they can be quite easily used with PyTorch, but that won't always be the case with your own custom datasets. However, what we're about to cover is just important to get an idea of what the computer vision workflow is, and then later on you can start to customize how you get your data in the right format to be used with the model. Then we have some different parameters here and whatnot. Let's just, rather than look at the documentation, if in doubt, code it out. So we'll be using Fashion MNIST, and we'll start by, I'm going to just put this here, from torchvision.datasets, and we'll put the link there, and we'll start by getting the training data. Set up training data. I'm just going to make some code cells here so that I can code in the middle of the screen. Set up training data. train data equals datasets.fashionMnist, because recall, we've already from Torch Vision, we don't need to import this again. I'm just doing it for demonstration purposes, but from Torch Vision, import datasets. So we can just call datasets.fashionMnist. And then we're going to type in root. See how the docstring comes up and tells us what's going on. I personally find this a bit hard to read in Google Colab. So if I'm looking up the documentation, I like to just go into here. But let's code it out. So root is going to be data. So where to download data to. We'll see what this does in a minute. Then we're going to go train. We want the training version of the data set. So as I said, a lot of the data sets that you find in torchvision.datasets have been formatted into training dataset and testing dataset already. So this boolean tells us, do we want the training dataset? So if that was false, we would get the testing dataset of FashionMnist. Do we want to download it? Do we want to download? Yes, no. So yes, we do. We're going to set that to true. Now, what sort of transform do we want to do? So because we're going to be downloading images, and what do we have to do to our images to use them with a machine learning model? We have to convert them into tensors. So I'm going to pass the transform to tensor, but we could also just go torchvision.transforms.toTensor. That would be the exact same thing as what we just did before. And then the target transform, do we want to transform the labels? No, we don't. We're going to see how they come, or the targets, sorry. PyTorch, this is another way, another naming convention, often uses target for the target that you're trying to predict. So using data to predict a target, which is I often use data to predict a label. They're the same thing. So how do we want to transform the data? And how do we want to transform the labels / targets? And then we're going to do the same for the test data. So we're going to go data sets. You might know what to do here. It's going to be the exact same code as above, except we're going to change one line. We want to store it in data. We want to download the training data set as false because we want the testing version. Do we want to download it? Yes, we do. Do we want to transform it, the data? Yes, we do. We want to use toTensor to convert our image data to tensors. And do we want to do a target transform? Well, no, we don't. We want to keep the label / the targets as they are. Let's see what happens when we run this. Downloading FashionMnist. Beautiful. So this is going to download all of the labels. What do we have? Train images, train labels, lovely. Test images, test labels, beautiful. So that's how quickly we can get a data set by using Torch Vision datasets. Now, if we have a look over here, we have a data folder because we set the root to be data. And then if we look what's inside here, we have FashionMnist, exactly what we wanted. Then we have the raw, and then we have a whole bunch of files here, which Torch Vision has converted into datasets for us. So let's get out of that. And this process would be much the same if we used almost any dataset in here. Of course, they might be slightly different depending on what the documentation says and depending on what the dataset is, but that is how easy torchvision.datasets makes it to practice on example computer vision datasets. So let's go back. Let's check out some parameters or some attributes of our data. How many samples do we have? So we'll check the lengths. So we have 60,000 training examples and 10,000 testing examples. So what we're going to be doing is we're going to be building a computer vision model to find patterns in the training data and then use those patterns to predict on the test data. And so let's see a first training example. See the first training example. So we can just index on the train data. Let's get the 0th index, and then we're going to have a look at the image and the label. Oh my goodness. Whole bunch of numbers. Now you see what the toTensor has done for us? So we've downloaded some images, and thanks to this Torch Vision transforms toTensor, how would we find the documentation for this? Well, we could go and see what this does. Transforms toTensor. We could go toTensor. There we go. What does this do? Convert a PIL image, so that's Python image library image or NumPy array to a tensor. This transform does not support torch script, so converts a pill image or NumPy array, height, width, color channels in the range 0 to 255 to a torch float tensor of shape. See here? This is what I was talking about, how PyTorch defaults with a lot of transforms to CHW. So color channels first, height, then width in the range of 0 to 1. So typically red, green, and blue values are between 0 and 255, but neural networks like things between 0 and 1. And in this case, it is now in the shape of color channels first, then height, then width. However, some other machine learning libraries prefer height, width, then color channels. Just keep that in mind. We're going to see this in practice later on. So we've got an image, we've got a label. Let's check out some more details about it. Remember how we discussed, oh, there's our label, by the way. So 9, we can go train data.classes, find some information about our class names. Class names. Beautiful. So number 9 would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this particular tensor seems to relate to an ankle boot. How would we find that out? Well, one second. I'm just going to show you one more thing. Class to IDX. Let's go train data.class to IDX. What does this give us? Class to IDX. This is going to give us a dictionary of different labels and their corresponding index. So if our machine learning model predicted 9 or class 9, we can convert that to ankle boot using this attribute of the train data. There are more attributes that you can have a look at if you like. You can go train data dot, and then I just push tab to find out a bunch of different things. You could go data, there's the data, that'll be the images, and then I believe you can also go targets. So targets, that's all the labels, which is one big long tensor. Now let's check the shape. Check the shape of our image. So image.shape and label.shape. What are we going to get from that? Oh, label doesn't have a shape. Why is that? Well, because it's only an integer. So, oh, beautiful. Look at that. So our image shape is we have a color channel of 1. So let me print this out in something prettier. Print image shape, which is going to be image shape. Remember how I said it's very important to be aware of the input and output shapes of your models and your data? It's all part of becoming one with the data. So that is what our image shape is. And then if we go next, this is print image label, which is label, but we'll index on class names for label. And then we'll do that. Wonderful. So our image shape is currently in the format of color channels, height, width. We've got a bunch of different numbers that's representing our image. It's black and white. It only has one color channel. Why do you think it only has one color channel? Well, because it's black and white. So if we jump back into the keynote, Fashion MNIST, we've already discussed this. Grayscale images have one color channel. So that means that for black, the pixel value is 0. And for white, it's some value for whatever color is going on here. So if it's a very high number, say it's 1, it's going to be pure white. If it's like 0.001, it might be a faint white pixel. But if it's exactly 0, it's going to be black. So color images have 3 color channels for red, green, and blue. Grayscale have 1 color channel. But I think we've done enough of visualizing our images as numbers. How about in the next video, we visualize our image as an image? I'll see you there. Welcome back. So in the last video, we checked the input-output shapes of our data, and we downloaded the Fashion MNIST dataset, which is comprised of images or grayscale images of t-shirts, trousers, pullovers, dress, coat, sandal, shirt, sneaker, bag, ankle boot. Now, we want to see if we can build a computer vision model to decipher what's going on in Fashion MNIST. So to separate, to classify different items of clothing based on their numerical representation. And part of becoming one with the data is, of course, checking the input-output shapes of it. So this is a Fashion MNIST dataset from Zalando Research. Now, if you recall, why did we look at our input and output shapes? Well, this is what we looked at before. We have 28 by 28 grayscale images that we want to represent as a tensor. We want to use them as input into a machine learning algorithm, typically a computer vision algorithm, such as a CNN. Then we want to have some sort of outputs that are formatted in the ideal shape that we'd like. So in our case, we have 10 different types of clothing. So we're going to have an output shape of 10. But our input shape is what? So by default, pytorch turns tensors into color channels first. So we have an input shape of none, 1, 28, 28. So none is going to be our batch size, which of course we can set that to whatever we'd like. And so our input shape format is in NCHW, or in other words, color channels first. But just remember, if you're working with some other machine learning libraries, you may want to use color channels last. So let's have a look at where that might be the case. We're going to visualize our images. So I'll make a little heading here, 1.2. Now, this is all part of becoming one with the data. Other words, understanding its input and output shapes, how many samples there are, what they look like. Visualize, visualize, visualize. Let's import matplotlib. I'm just going to add a few code cells here. Import matplotlib.pyplot, pyplot as PLT. Now, let's create our image and label. Is our train data 0? And we're going to print the image shape so we can understand what inputs are going into our matplotlib function. And then we're going to go plot.imShow, and we're going to pass in our image and see what happens. Because recall, what does our image look like? Image. Our image is this big tensor of numbers. And we've got an image shape, 128, 128. Now, what happens if we call plot.imShow? What happens there? Oh, we get an error. Invalid shape, 128, 128 for image data. Now, as I said, this is one of the most common errors in machine learning is a shape issue. So the shape of your input tensor doesn't match the expected shape of that tensor. So this is one of those scenarios where our data format, so color channels first, doesn't match up with what matplotlib is expecting. So matplotlib expects either just height and width, so no color channel for grayscale images, or it also expects the color channels to be last. So we'll see that later on, but for grayscale, we can get rid of that extra dimension by passing in image.squeeze. So do you recall what squeeze does? It's going to remove that singular dimension. If we have a look at what goes on now, beautiful, we get an ankle boot. Well, that's a very pixelated ankle boot, but we're only dealing with 28 by 28 pixels, so not a very high definition image. Let's add the title to it. We're going to add in the label. Beautiful. So we've got the number 9 here. So where if we go up to here, that's an ankle boot. Now let's plot this in grayscale. How might we do that? We can do the same thing. We can go plot plt.imShow. We're going to pass in image.squeeze. And we're going to change the color map. CMap equals gray. So in matplotlib, if you ever have to change the colors of your plot, you want to look into the CMap property or parameter, or sometimes it's also shortened to just C. But in this case, imShow is CMap. And we want a plot title. And we're going to put in class names and the label integer here. So if we have a look at it now, we have an ankle boot, and we can remove the axes too if we wanted to. Plot.axis, and turn that off. That's going to remove the axis. So there we go, that's the type of images that we're dealing with, but that's only a singular image. How about we harness the power of randomness and have a look at some random images from our data set. So, how would we do this? Let's go plot more images. We'll set a random seed. So you and I are both looking at as similar as possible images, 42. Now we'll create a plot by calling plot.figure, and we're going to give it a size. We might create a 9 by 9 grid. So we want to see 9 random images from our data set. So rows, cols, or sorry, maybe we'll do 4 by 4. That'll give us 16. We're going to go for I in range, and we're going to go 1 to rows times columns plus 1. So we can print I. What's that going to give us? We want to see 16 images, or thereabouts. So 16 random images, but used with a manual seed of 42 of our data set. This is one of my favorite things to do with any type of data set that I'm looking at, whether it be text, image, audio, doesn't matter. I like to randomly have a look at a whole bunch of samples at the start so that I can become one with the data. With that being said, let's use this loop to grab some random indexes. We can do so using torch's rand int, so random integer, between 0 and length of the training data. This is going to give us a random integer in the range of 0 and however many training samples we have, which in our case is what? 60,000 or thereabouts. So we want to create the size of 1, and we want to get the item from that so that we have a random index. What is this going to give us? Oh, excuse me, maybe we print that out. There we go. So we have random images. Now, because we're using manual seed, it will give us the same numbers every time. So we have 37542, 37542. And then if we just commented out the random seed, we'll get different numbers every time. But this is just to demonstrate. We'll keep the manual seed there for now. You can comment that out if you want different numbers or different images, different indexes each time. So we'll create the image and the label by indexing on the training data at the random index that we're generating. And then we'll create our plot. So fig, or we'll add a subplot. Fig add subplot. And we're going to go rows, cols, I. So at the ith index, we're going to add a subplot. Remember, we set rows and columns up to here. And then we're going to go plt.imshow. We're going to show what? We're going to show our image, but we have to squeeze it to get rid of that singular dimension as the color channel. Otherwise, we end up with an issue with matplotlib. We're going to use a color map of gray so it looks like the image we plotted above. And then for our title, it's going to be our class names indexed with our label. And then we don't want the axes because that's going to clutter up our plot. Let's see what this looks like. Oh my goodness, look at that. It worked first go. Usually visualizations take a fair bit of trial and error. So we have ankle boots, we have shirts, we have bags, we have ankle boots, sandal, shirt, pullover. Oh, do you notice something about the data set right now? Pullover and shirt. To me, they look quite similar. Do you think that will cause an issue later on when our model is trying to predict between a pullover and a shirt? How about if we look at some more images? We'll get rid of the random seed so we can have a look at different styles. So we have a sandal, ankle boot, coat, t-shirt, top, shirt. Oh, is that a little bit confusing that we have a class for t-shirt and top and shirt? Like, I'm not sure about you, but what's the difference between a t-shirt and a shirt? This is just something to keep in mind. As a t-shirt and top, does that look like it could be maybe even a dress? Like the shape is there? So this is just something to keep in mind going forward. Chances are if we get confused on our, like you and I looking at our data set, if we get confused about different samples and what they're labeled with, our model might get confused later on. So let's have a look at one more and then we'll go into the next video. So we have sneaker, trouser, shirt, sandal, dress, pullover, bag, t-shirt. Oh, that's quite a difficult one. Doesn't look like there's even much going on in that image. But the whole premise of building machine learning models to do this would be, could you write a program that would take in the shapes of these images and write a rule-based program that would go, hey, if it's look like a rectangle with a buckle in the middle, it's probably a bag. I mean, you probably could after a while, but I prefer to write machine learning algorithms to figure out patterns in data. So let's start moving towards that. We're now going to go on figuring out how we can prepare this data to be loaded into a model. I'll see you there. All right. So we've got 60,000 images of clothing that we'd like to build a computer vision model to classify into 10 different classes. And now that we've visualized a fair few of these samples, do you think that we could model these with just linear lines, so straight lines? Or do you think we'll need a model with nonlinearity? So I'm going to write that down. So do you think these items of clothing, images, could be modeled with pure linear lines? Or do you think we'll need nonlinearity? Don't have to answer that now. We could test that out later on. You might want to skip ahead and try to build a model yourself with linear lines or nonlinearities. We've covered linear lines and nonlinearities before, but let's now start to prepare our data even further to prepare data loader. So right now, our data is in the form of PyTorch datasets. So let's have a look at it. Train data. There we go. So we have data set, which is of fashion MNIST. And then if we go test data, we see a similar thing, except we have a different number of data points. We have the same transform on each, we've turned them into tensors. So we want to convert them from a data set, which is a collection of all of our data, into a data loader. Recall that a data loader turns our data set into a Python iterable. So I'm going to turn this into Markdown. Beautiful. More specifically, can I spell right? It doesn't really matter. We want to just code right. We're not here to learn spelling. We want to turn our data into batches or mini batches. Why would we do this? Well, we may get away with it by building a model to look at all 60,000 samples of our current data set because it's quite small. It's only comprised of images of 28 by 28 pixels. And when I say quite small, yes, 60,000 images is actually quite small for a deep learning scale data set. Modern data sets could be in the millions of images. But if our computer hardware was able to look at 60,000 samples of 28 by 28 at one time, it would need a fair bit of memory. So we have RAM space up here, we have GPU memory, we have compute memory, but chances are that it might not be able to store millions of images in memory. So what you do is you break a data set from, say, 60,000 into groups of batches or mini batches. So we've seen batch size before. Why would we do this? Well, one, it is more computationally efficient, as in your computing hardware may not be able to store in memory at 60,000 images in one hit. So we break it down to 32 images at a time. This would be batch size of 32. Now, again, 32 is a number that you can change. 32 is just a common batch size that you'll see with many beginner-style problems. As you go on, you'll see different batch sizes. This is just to exemplify the concept of mini batches, which is very common in deep learning. And why else would we do this? The second point, or the second main point, is it gives our neural network more chances to update its gradients per epoch. So what I mean by this will make more sense when we write a training loop, but if we were to just look at 60,000 images at one time, we would, per epoch, so per iteration through the data, we would only get one update per epoch across our entire data set. Whereas if we look at 32 images at a time, our neural network updates its internal states, its weights, every 32 images, thanks to the optimizer. This will make a lot more sense once we write our training loop. But these are the two of the main reasons for turning our data into mini batches in the form of a data loader. Now, if you'd like to learn more about the theory behind this, I would highly recommend looking up Andrew Ong mini batches. There's a great lecture on that. So yeah, large-scale machine learning, mini batch gradient descent, mini batch gradient descent. Yeah, that's what it's called, mini batch gradient descent. If you look up some results on that, you'll find a whole bunch of stuff. I might just link this one. I'm going to pause that. I'm going to link this in there. So for more on mini batches, see here. Now, to see this visually, I've got a slide prepared for this. So this is what we're going to be working towards. There's our input and output shapes. We want to create batch size of 32 across all of our 60,000 training images. And we're actually going to do the same for our testing images, but we only have 10,000 testing images. So this is what our data set's going to look like batched. So we're going to write some code, namely using the data loader from torch.utils.data. We're going to pass it a data set, which is our train data. We're going to give it a batch size, which we can define as whatever we want. For us, we're going to use 32 to begin with. And we're going to set shuffle equals true if we're using the training data. Why would we set shuffle equals true? Well, in case our data set for some reason has order, say we had all of the pants images in a row, we had all of the t-shirt images in a row, We had all the sandal images in a row. We don't want our neural network to necessarily remember the order of our data. We just want it to remember individual patterns between different classes. So we shuffle up the data, we mix it up. And then it looks something like this. So we might have batch number 0, and then we have 32 samples. Now, I ran out of space when I was creating these, but we got ... That was fun. Up to 32. So this is setting batch size equals 32. So we look at 32 samples per batch. We mix all the samples up, and we go batch, 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 and we'll have however many batches we have, we'll have number of samples divided by the batch size. So 60,000 divided by 32, what's that, 1,800 or something like that? So this is what we're going to be working towards. I did want to write some code in this video, but I think to save it getting too long, we're going to write this code in the next video. If you would like to give this a go on your own, here's most of the code we have to do. So there's the train data loader. Do the same for the test data loader. And I'll see you in the next video, and we're going to batchify our fashion MNIST dataset. Welcome back. In the last video, we had a brief overview of the concept of mini batches. And so rather than our computer looking at 60,000 images in one hit, we break things down. We turn it into batches of 32. Again, the batch size will vary depending on what problem you're working on, but 32 is quite a good value to start with and try out. And we do this for two main reasons. If we jump back to the code, why would we do this? It is more computationally efficient. So if we have a GPU with, say, 10 gigabytes of memory, it might not be able to store all 60,000 images in one hit. In our data set, because it's quite small, it may be able to, but it's better practice for later on to turn things into mini batches. And it also gives our neural network more chances to update its gradients per epoch, which will make a lot more sense once we write our training loop. But for now, we've spoken enough about the theory. Let's write some code to do so. So I'm going to import data loader from torch.utils.data, import data loader. And this principle, by the way, preparing a data loader, goes the same for not only images, but for text, for audio, whatever sort of data you're working with. Mini batches will follow you along, or batches of data will follow you along throughout a lot of different deep learning problems. So set up the batch size hyperparameter. Remember, a hyperparameter is a value that you can set yourself. So batch size equals 32, and it's practice. You might see it typed as capitals. You won't always see it, but you'll see it quite often, a hyperparameter typed as capitals. And then we're going to turn data sets into iterables. So batches. So we're going to create a train data loader here of our fashion MNIST dataset. We're going to use data loader. We're going to see what the docstring is. Or actually, let's look at the documentation. Torch data loader. This is some extra curriculum for you too, by the way, is to read this data page, torch.utils.data, because no matter what problem you're going with deep learning or PyTorch, you're going to be working with data. So spend 10 minutes just reading through here. I think I might have already assigned this, but this is just so important that it's worth going through again. Read through all of this. Even if you don't understand all of it, what's going on, it helps you know where to look for certain things. So what does it take? Data loader takes a data set. We need to set the batch size to something. It's the default of 1. That means that we would create a batch of 1 image at a time in our case. Do we want to shuffle it? Do we want to use a specific sampler? There's a few more things going on. Number of workers. Number of workers stands for how many cores on our machine do we want to use to load data. Generally, the higher the better for this one. But we're going to keep most of these as the default because most of them are set to pretty good values to begin with. I'll let you read more into the other parameters here. We're going to focus on the first 3. Data set, batch size, and shuffle, true or false. Let's see what we can do. So data set equals our train data, which is 60,000 fashion MNIST. And then we have a batch size, which we're going to set to our batch size hyperparameter. So we're going to have a batch size of 32. And then finally, do we want to shuffle the training data? Yes, we do. And then we're going to do the same thing for the test data loader, except we're not going to shuffle the test data. Now you can shuffle the test data if you want, but in my practice, it's actually easier to evaluate different models when the test data isn't shuffled. So you shuffle the training data to remove order, and so your model doesn't learn order. But for evaluation purposes, it's generally good to have your test data in the same order because our model will never actually see the test data set during training. We're just using it for evaluation. So the order doesn't really matter of the test data loader. It's just easier if we don't shuffle it, because then if we evaluate it multiple times, it's not being shuffled every single time. So let's run that. And then we're going to check it out, our train data loader and our test data loader. Beautiful. We've got instances of torch utils data loader. And now let's check out what we've created, hey? I always like to print different attributes of whatever we make. Check out what we've created. This is all part of becoming one with the data. So print F, I'm going to go data loaders, and then pass in, this is just going to output basically the exact same as what we've got above, test data loader. And we can also see what attributes we can get from each of these by going train data loader. I don't need caps lock there. Train data loader, full stop, and then we can go tab. We've got a whole bunch of different attributes. We've got a batch size, we've got our data set. Do we want to drop the last, as in if our batch size overlapped with our 60,000 samples, do we want to get rid of the last batch? Say for example, the last batch only had 10 samples. Do we want to just drop that? Do we want to pin the memory? That's going to help later on if we wanted to load our data faster. A whole bunch of different stuff here. If you'd like to research more, you can find all the stuff about what's going on here in the documentation. But let's just keep pushing forward. What else do we want to know? So let's find the length of the train data loader. We will go length, train data loader. So this is going to tell us how many batches there are. Batches of, which of course is batch size. And we want print length of test data loader. We want length test data loader batches of batch size. ... So let's find out some information. What do we have? Oh, there we go. So just we're seeing what we saw before with this one, but this is more interesting here. Length of train data loader. Yeah, we have about 1,875 batches of 32. So if we do 60,000 training samples divided by 32, yeah, it comes out to 1875. And if we did the same with 10,000 for testing samples of 32, it comes out at 313. This gets rounded up. So this is what I meant, that the last batch will have maybe not 32 because 32 doesn't divide evenly into 10,000. But that's okay. And so this means that our model is going to look at 1,875 individual batches of 32 images rather than just one big batch of 60,000 images. Now, of course, the number of batches we have will change if we change the batch size. So we have 469 batches of 128. And if we reduce this down to 1, what do we get? We have a batch per sample. So 60,000 batches of 1, 10,000 batches of 1, but we're going to stick with 32. But now let's visualize. So we've got them in train data loader. How would we visualize a batch or a single image from a batch? So let's show a sample. I'll show you how you can interact with a data loader. We're going to use randomness as well. So we'll set a manual seed and then we'll get a random index. Random IDX equals torch rand int. We're going to go from 0 to length of train features batch. Oh, where did I get that from? Excuse me, getting ahead of myself here. I want to check out what's inside the training data loader. We'll check out what's inside the training data loader because the test data loader is going to be similar. So we want the train features batch. So I say features as in the images themselves, and the train labels batch is going to be the labels of our data set or the targets in PyTorch terminology. So next iter data loader. So because our data loader has 1,875 batches of 32, we're going to turn it into an iterable with iter, and we're going to get the next batch with next. And then we can go here, train features batch.shape, and we'll get train labels batch.shape. What do you think this is going to give us? Well, there we go. Look at that. So we have a tensor. Each batch we have 32 samples, so this is batch size, and this is color channels, and this is height, and this is width. And then we have 32 labels associated with the 32 samples. Now, where have we seen this before? If we go back through our keynote, input and output shapes. So we have shape equals 32, 28, 28, 1. So this is color channels last, but ours is currently in color channels first. Now, again, I sound like a broken record here, but these will vary depending on the problem you're working with. If we had larger images, what would change? Well, the height and width dimensions would change. If we had color images, the color dimension would change. But the premise is still the same. We're turning our data into batches so that we can pass that to a model. Let's come back. Let's keep going with our visualization. So we want to visualize one of the random samples from a batch. And then we're going to go image label equals train features batch. And we're going to get the random IDX from that. And we'll get the train labels batch. And we'll get the random IDX from that. So we're matching up on the, we've got one batch here, train features batch, train labels batch. And we're just getting the image and the label at a random index within that batch. So, oh, excuse me, I need to set this equal there. And then we're going to go plt.imShow. What are we going to show? We're going to show the image, but we're going to have to squeeze it to remove that singular dimension. And then we'll set the CMAP equal to gray. And then we'll go plt.title. We'll set the title, which is going to be the class names indexed by the label, integer. And then we can turn off the accesses. You can use off here, or you can use false. Depends on what you'd like to use. Let's print out the image size, because you can never know enough about your data. And then print. Let's also get the label. Label and label shape or label size. Our label will be just a single integer, so it might not have a shape. But that's okay, let's have a look. Oh, bag. See, look, that's quite hard to understand. I wouldn't be able to detect that that's a bag. Can you tell me that you could write a program to understand that? That just looks like a warped rectangle to me. But if we had a look at another one, we'll get another random, oh, we've got a random seed, so it's going to produce the same image each time. So we have a shirt, okay, shirt. So we see the image size there, 128, 28. Now, recall that the image size is, it's a single image, so it doesn't have a batch dimension. So this is just color channels, height, width. We'll go again. Label 4, which is a coat. And we could keep doing this to become more and more familiar with our data, but these are all from this particular batch that we created here. Coat, and we'll do one more, another coat. We'll do one more just to make sure it's not a coat. There we go, we got a bag. Beautiful. So we've now turned our data into data loaders. So we could use these to pass them into a model, but we don't have a model. So I think it's time in the next video, we start to build model 0. We start to build a baseline. I'll see you in the next video. Welcome back. So in the last video, we got our data sets or our data set into data loaders. So now we have 1,875 batches of 32 images, or for the training data set, rather than 60,000 in one big data set. And we have 313 batches of 32 for the test data set. And then we learned how to visualize it from a batch. And we saw that we have still the same image size, one color channel, 28, 28. All we've done is we've turned them into batches so that we can pass them to our model. And speaking of model, let's have a look at our workflow. Where are we up to? Well, we've got our data ready. We've turned it into tensors through a combination of torch vision transforms, torch utils data.dataset. We didn't have to use that one because torch vision.datasets did it for us with the fashion MNIST dataset. But we did use that one. We did torch utils.data loader to turn our data sets into data loaders. Now we're up to building or picking a pre-trained model to suit your problem. So let's start simply. Let's build a baseline model. And this is very exciting because we're going to build our first model, our first computer vision model. Albeit a baseline, but that's an important step. So I'm just going to write down here. When starting to build a series of machine learning modeling experiments, it's best practice to start with a baseline model. So I'm going to turn this into Markdown. A baseline model. So a baseline model is a simple model you will try and improve upon with subsequent models. Models/experiments. So you start simply, in other words, start simply and add complexity when necessary. Because neural networks are pretty powerful, right? And so they have a tendency to almost do too well on our data set. That's a concept known as overfitting, which we'll cover a little bit more later. But we build a simple model to begin with, a baseline. And then our whole goal will be to run experiments according to the workflow, improve through experimentation. Again, this is just a guide. It's not set in stone, but this is the general pattern of how things go. Get data ready, build a model, fit the model, evaluate, improve the model. So the first model that we build is generally a baseline. And then later on, we want to improve through experimentation. So let's start building a baseline. But I'm going to introduce to you a new layer that we haven't seen before, and that is creating a flatten layer. Now, what is a flatten layer? Well, this is best seen when we code it out. So let's create a flatten model, which is just going to be nn.flatten. And where could we find the documentation for this? We go nn flatten. Flatten in PyTorch. What does it do? Flattens a contiguous range of dims into a tensor for use with sequential. So there's an example there, but I'd rather, if in doubt, code it out. So we'll create the flatten layer, and of course, all nn.flatten or nn.modules could be used as a model on their own. So we're going to get a single sample. So x equals train features batch. Let's get the first one, 0. What does this look like? So it's a tensor. X. Maybe we get the shape of it as well. X shape. What do we get? There we go. So that's the shape of X. Keep that in mind when we pass it through the flatten layer. Do you have an inkling of what flatten might do? So our shape to begin with is what? 128, 28. Now let's flatten the sample. So output equals, we're going to pass it to the flatten model, X. So this is going to perform the forward pass internally on the flatten layer. So perform forward pass. Now let's print out what happened. Print out what happened. Print shape before flattening equals x.shape. And we're going to print shape after flattening equals output.shape. So we're just taking the output of the flatten model and printing its shape here. Oh, do you notice what happened? Well, we've gone from 128.28 to 1784. Wow, what does the output look like? Output. Oh, the values are now in all one big vector. And if we squeeze that, we can remove the extra dimension. So we've got one big vector of values. Now, where did this number come from? Well, if we take this, and this is, what shape is it? We've got color channels, we've got height, we've got width, and now we've flattened it to be color channels, height, width. So we've got one big feature vector because 28 by 28 equals what? We've got one value per pixel, 784. One value per pixel in our output vector. Now, where did we see this before? If we go back to our keynote, if we have a look at Tesla's, takes 8 cameras and then it turns it into a 3-dimensional vector space. Vector space. So that's what we're trying to do here. We're trying to encode whatever data we're working with. In Tesla's case, they have 8 cameras. Now theirs has more dimensions than ours because they have the time aspect because they're dealing with video and they have multiple different camera angles. We're just dealing with a single image here. But regardless, the concept is the same. We're trying to condense information down into a single vector space. And so if we come back to here, why might we do this? Well, it's because we're going to build a baseline model and we're going to use a linear layer as the baseline model. And the linear layer can't handle multi-dimensional data like this. We want it to have a single vector as input. Now this will make a lot more sense after we've coded up our model. So let's do that. From torch, import NN. We're going to go class, fashion, mnist, model v0. We're going to inherit from nn.module. And inside here, we're going to have an init function in the constructor. We're going to pass in self. We're going to have an input shape, which we'll use a type hint, which will take an integer. Because remember, input shape is very important for machine learning models. We're going to define a number of hidden units, which will also be an integer. And then we're going to define our output shape, which will be, what do you think our output shape will be? How many classes are we dealing with? We're dealing with 10 different classes, so our output shape will be, I'll save that for later on. I'll let you guess for now, or you might already know. We're going to initialize it. And then we're going to create our layer stack. Self.layerStack equals nn.sequential. Recall that sequential, whatever you put inside sequential, if data goes through sequential, it's going to go through it layer by layer. So let's create our first layer, which is going to be nn.flatten. So that means anything that comes into this first layer, what's going to happen to it? It's going to flatten its external dimensions here. So it's going to flatten these into something like this. So we're going to flatten it first, flatten our data. And then we're going to pass in our linear layer. And we're going to have how many in features? This is going to be input shape, because we're going to define our input shape here. And then we're going to go out features equals hidden units. And then we're going to create another linear layer here. And we're going to set up in features equals hidden units. Why are we doing this? And then out features equals output shape. Why are we putting the same out features here as the in features here? Well, because subsequent layers, the input of this layer here, its input shape has to line up with the output shape of this layer here. Hence why we use out features as hidden units for the output of this nn.linear layer. And then we use in features as hidden units for the input value of this hidden layer here. So let's keep going. Let's go def, we'll create the forward pass here, because if we subclass nn.module, we have to override the forward method. The forward method is going to define what? It's going to define the forward computation of our model. So we're just going to return self.layerStack of x. So our model is going to take some input, x, which could be here, x. In our case, it's going to be a batch at a time. And then it's going to pass each sample through the flatten layer. It's going to pass the output of the flatten layer to this first linear layer. Then it's going to pass the output of this linear layer to this linear layer. So that's it. Our model is just two linear layers with a flatten layer. The flatten layer has no learnable parameters. Only these two do. And we have no nonlinearities. So do you think this will work? Does our dataset need nonlinearities? Well, we can find out once we fit our model to the data. But let's set up an instance of our model. So torch.manual seed. Let's go set up model with input parameters. So we have model 0 equals fashion mnist model, which is just the same class that we wrote above. And here's where we're going to define the input shape equals 784. Where did I get that from? Well, that's here. That's 28 by 28. So the output of flatten needs to be the input shape here. So we could put 28 by 28 there, or we're just going to put 784 and then write a comment here. This is 28 by 28. Now, if we go, I wonder if nn.linear will tell us, nn.linear will tell us what it expects as in features. Size of each input sample, shape, where star means any number of dimensions including none, in features, linear weight, Well, let's figure it out. Let's see what happens. If in doubt, code it out, hey? We'll see what we can do. Hidden units equals, let's go with 10 to begin with. How many units in the hidden layer? And then the output shape is going to be what? Output shape is length of class names, which will be 1 for every class. Beautiful. And now let's go model 0. We're going to keep it on the CPU to begin with. We could write device agnostic code, but to begin, we're going to send it to the CPU. I might just put that up here actually, to CPU. And then let's have a look at model 0. Wonderful. So we can try do a dummy forward pass and see what happens. So let's create dummy x equals torch rand. We'll create it as the same size of an image, just a singular image. So this is going to be a batch of 1, color channel 1, height 28, height 28. And we're going to go model 0 and pass through dummy x. So this is going to send dummy x through the forward method. Let's see what happens. Okay, wonderful. So we get an output of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 logits. Beautiful. That's exactly what we want. So we have 1 logit value per class that we have. Now, what would happen if we got rid of flatten? And then we ran this, ran this, ran this. What do we get? Oh, mat1 and mat2 shapes cannot be multiplied. So we have 28 by 28 and 7. Okay, what happens if we change our input shape to 28? We're getting shape mismatches here. What happens here? Oh, okay, we get an interesting output. But this is still not the right shape, is it? So that's where the flatten layer comes in. What is the shape of this? Oh, we get 1, 1, 28, 10. Oh, so that's why we put in flatten, so that it combines it into a vector. So we get rid of this. See, if we just leave it in this shape, we get 28 different samples of 10, which is not what we want. We want to compress our image into a singular vector and pass it in. So let's reinstantiate the flatten layer. And let's make sure we've got the right input shape here, 28 by 28. And let's pass it through. Torch size 110. That's exactly what we want, 1 logit per class. So this can be a bit fiddly when you first start, but it's also a lot of fun once you get it to work. And so just keep that in mind. I showed you what it looks like when you have an error. One of the biggest errors that you're going to face in machine learning is different tensor shape mismatches. So just keep in mind the data that you're working with, and then have a look at the documentation for what input shape certain layers expect. So with that being said, I think it's now time that we start moving towards training our model. I'll see you in the next video. Welcome back. In the last video, we created model 0, which is going to be our baseline model for our computer vision problem of detecting different types of clothing in 28 by 28 grayscale images. And we also learned the concept of making sure we rehashed on the concept of making sure our input and output shapes line up with where they need to be. We also did a dummy forward pass with some dummy data. This is a great way to troubleshoot to see if your model shapes are correct, if they come out correctly, and if the inputs are lining up with where they need to be. And just to rehash on what our model is going to be, or what's inside our model, if we check model 0 state dict, what we see here is that our first layer has a weight tensor. It also has a bias, and our next layer has a weight tensor, and it also has a bias. So these are of course initialized with random values, but the whole premise of deep learning and machine learning is to pass data through our model and use our optimizer to update these random values to better represent the features in our data. And I keep saying features, but I just want to rehash on that before we move on to the next thing. Feature in data could be almost anything. So for example, the feature of this bag could be that it's got a rounded handle at the top. It has an edge over here. It has an edge over there. Now, we aren't going to tell our model what features to learn about the data. The whole premise of it is the whole fun, the whole magic behind machine learning is that it figures out what features to learn. And so that is what the weights and bias matrices or tensors will represent, is different features in our images. And there could be many because we have 60,000 images of 10 classes. So let's keep pushing forward. It's now time to set up a loss function and an optimizer. Speaking of optimizers, so 3.1, set up loss, optimizer, and evaluation metrics. Now, recall in Notebook 2, I'm going to turn this into Markdown. We created, oh, I don't need an emoji there. So this is, by the way, we're just moving through this workflow. We've got our data ready into tensors. We've built a baseline model. It's now time to pick a loss function and an optimizer. So if we go back to Google Chrome, let's write here, loss function. What's our loss function going to be? Since we're working with multi-class data, our loss function will be nn.cross-entropy loss. And our optimizer, we've got a few options here with the optimizer, but we've had practice in the past with SGD, which stands for stochastic gradient descent, and the atom optimizer. So our optimizer, let's just stick with SGD, which is kind of the entry-level optimizer, torch optim SGD for stochastic gradient descent. And finally, our evaluation metric, since we're working on a classification problem, let's use accuracy as our evaluation metric. So recall that accuracy is a classification evaluation metric. Now, where can we find this? Well, if we go into learnpytorch.io, this is the beauty of having online reference material. In here, neural network classification with PyTorch. In this notebook, section 02, we created, do we have different classification methods? Yes, we did. So we've got a whole bunch of different options here for classification evaluation metrics. We've got accuracy, precision, recall, F1 score, a confusion matrix. Now we have some code that we could use. If we wanted to use torch metrics for accuracy, we could. And torch metrics is a beautiful library that has a lot of evaluation. Oh, it doesn't exist. What happened to torch metrics? Maybe I need to fix that link. Torch metrics has a whole bunch of different PyTorch metrics. So very useful library. But we also coded a function in here, which is accuracy FN. So we could copy this straight into our notebook here. Or I've also, if we go to the PyTorch Deep Learning GitHub, I'll just bring it over here. I've also put it in helperfunctions.py. Now this is a script of common functions that we've used throughout the course, including if we find accuracy function here. Calculate accuracy. Now, how would we get this helper functions file, this Python file, into our notebook? One way is to just copy the code itself straight here. But let's import it as a Python script. So import request, then we're going to go from pathlib import path. So we want to download, and this is actually what you're going to see very common practice in larger Python projects, especially deep learning and machine learning projects, is different functionality split up in different Python files. And that way you don't have to keep rewriting the same code over and over again. Like, you know how we've written a training and testing loop a fair few times? Well, if we've written it once and it works, we might want to save that to a .py file so we can import it later on. But let's now write some code to import this helper functions .py file into our notebook here. So download helper functions from Learn PyTorch repo. So we're going to check if our helper functions .py, if this already exists, we don't want to download it. So we'll print helper functions.py already exists, skipping download, dot. And we're going to go else here. If it doesn't exist, so we're going to download it, downloading helper functions.py, and we're going to create a request here with the request library equals requests.get. Now, here's where we have to pass in the URL of this file. It's not this URL here. When dealing with GitHub, To get the actual URL to the files, many files, you have to click the raw button. So I'll just go back and show you. Click raw here, and we're going to copy this raw URL. See how it's just text here? This is what we want to download into our Colab notebook. And we're going to write it in there. Request equals request.get. And we're going to go with open. And here's where we're going to save our helper functions.py. We're going to write binary as file. F is for file. We're going to go f.write request.content. So what this is saying is Python is going to create a file called helperfunctions.py and give it write binary permissions as f. F is for file, short for file. And then we're going to say f.write, hey, request, get that information from helperfunctions.py here and write your content to this file here. So let's give that a shot. Beautiful. So downloading helperfunctions.py. Let's have a look in here. Do we have helperfunctions.py? Yes, we do. Wonderful. So now we can import our accuracy function. Where is it? There we go. Import accuracy function. So this is very common practice when writing lots of Python code, is to put helper functions into .py scripts. So let's import the accuracy metric. Accuracy metric from helper functions. Of course, we could have used torch metrics as well. That's another perfectly valid option, but I just thought I'd show you what it's like to import your own helper function script. Of course, you can customize helperfunctions.py to have whatever you want in there. So see this, we've got from helper functions, import accuracy function. What's this saying? Could not be resolved. Is this going to work? It did. And we can go accuracy function. Do we get a docstring? Seems like Colab isn't picking things up, but that's all right. It looks like it still worked. We'll find out later on if it actually works when we train our model. So set up loss function and optimizer. So I'm going to set up the loss function equals nn.crossEntropy loss. And I'm going to set up the optimizer here as we discussed before as torch.optim.sgd for stochastic gradient descent. The parameters I want to optimize are the parameters from model 0, our baseline model, which we had a look at before, which are all these random numbers. We'd like our optimizer to tweak them in some way, shape, or form to better represent our data. And then I'm going to set the learning rate here. How much should they be tweaked each epoch? I'm going to set it to 0.1. Nice and high because our data set is quite simple. It's 28 by 28 images. There are 60,000 of them. But again, if this doesn't work, we can always adjust this and experiment. So let's run that. We've got a loss function. Is this going to give me a docstring? There we go. So calculates accuracy between truth and predictions. Now, where does this docstring come from? Well, let's have a look. Helper functions. That's what we wrote before. Good on us for writing good docstrings. Accuracy function. Well, we're going to test all these out in the next video when we write a training loop. So, actually, I think we might do one more function before we write a training loop. How about we create a function to time our experiments? Yeah, let's give that a go in the next video. I'll see you there. Welcome back. In the last video, we downloaded our helperfunctions.py script and imported our accuracy function that we made in Notebook 2. But we could really beef this up, our helperfunctions.py file. We could put a lot of different helper functions in there and import them so we didn't have to rewrite them. That's just something to keep in mind for later on. But now let's create a function to time our experiments. So creating a function to time our experiments. So one of the things about machine learning is that it's very experimental. You've probably gathered that so far. So let's write here. So machine learning is very experimental. Two of the main things you'll often want to track are, one, your model's performance, such as its loss and accuracy values, etc. And two, how fast it runs. So usually you want a higher performance and a fast model. That's the ideal scenario. However, you could imagine that if you increase your model's performance, you might have a bigger neural network, it might have more layers, it might have more hidden units, it might degrade how fast it runs because you're simply making more calculations. So there's often a trade-off between these two. And how fast it runs will really be important if you're running a model, say, on the internet, or say on a dedicated GPU, or say on a mobile device. So these are two things to really keep in mind. So because we're tracking our model's performance with our loss value and our accuracy function, let's now write some code to check how fast it runs. And I did on purpose above, I kept our model on the CPU. So we're also going to compare later on how fast our model runs on the CPU versus how fast it runs on the GPU. So that's something that's coming up. Let's write a function here. We're going to use the timeIt module from Python. So from timeIt, import the default timer as, I'm going to call it timer. So if we go Python default timer, do we get the documentation for, here we go, timeIt. So do we have default timer? Wonderful. So the default timer, which is always time.perf counter, you can read more about Python timing functions in here, but this is essentially just going to say, hey, this is the exact time that our code started, and then we're going to create another stop for when our code stopped, and then we're going to compare the start and stop times, and that's going to basically be how long our model took to train. So we're going to go def print train time, and this is just going to be a display function. So start, we're going to get the float, type hint by the way, start and end time. So the essence of this function will be to compare start and end time, and we're going to set the torch or the device here. We'll pass this in as torch.device, and we're going to set that default to none because we want to compare how fast our model runs on different devices. So I'm just going to write a little doc string here. Prints difference between start and end time. And then of course we could add more there for the arguments, but that's a quick one-liner. Tell us what our function does. So total time equals end minus start. And then print, we're going to write here, train time on whichever device we're using. Might be CPU, might be GPU. Total time equals, we'll go to 3, and we'll say seconds. 3 decimal places, that is, and return total time. Beautiful. So, for example, we could do start time equals timer, and then end time equals timer. And then we can put in here some code between those two. And then if we go print train, oh, maybe we need timer like this. We'll find out. If in doubt, code it out, you know. We'll see if it works. Start equals start time, and end equals end time, and device equals, we're running on the CPU right now. CPU. Let's see if this works. Wonderful. So it's a very small number here. So train time on CPU, very small number because the start time is basically on this exact line. Comment basically takes no time to run, and then end time is on here. We get 3.304 times 10 to the power of -5. So quite a small number, but if we put some modeling code in here, it's going to measure the start time of this cell. It's going to model our code in there. Then we have the end time, and then we find out how long our model took to train. So with that being said, I think we've got all of the pieces of the puzzle for creating some training and testing functions. So we've got a loss function, we've got an optimizer, we've got a valuation metric, we've got a timing function, we've got a model, we've got some data. How about we train our first baseline computer vision model in the next video? I'll see you there. Good morning. Well, might not be morning wherever you are in the world. It's nice and early here. I'm up recording some videos because we have a lot of momentum going with this. But look at this. I took a little break last night. I have a runtime disconnected, but this is just what's going to happen if you're using Google Colab. Since I use Google Colab Pro, completely unnecessary for the course, but I just found it worth it for how much I use Google Colab. I get longer idle timeouts. So that means that my Colab notebook will stay persistent for a longer time. But Of course, overnight, it's going to disconnect. So I click reconnect. And then if I want to get back to wherever we were, because we downloaded some data from torchvision.datasets, I have to rerun all of these cells. So a nice shortcut, we might have seen this before, is to just come down to where we were. And if all the code above works, oh, there we go. I wrote myself some notes of where we're up to. Let's go run before. So this is going to run all the cells above, and we're up to here. 3.3, creating a training loop and training a model on batches of data. So that's going to be a little bit interesting. And I wrote myself another reminder here. This is a little bit of behind the scenes. The optimizer will update a model's parameters once per batch rather than once per epoch. So let's hold myself to that note and make sure I let you know. So we'll go make another title here. Let's go creating a training loop and training a model on batches of data. So something a little bit different to what we may have seen before if we haven't created batches of data using data loader. And recall that just up above here, we've got something like 1800 there we go. So we've split our data into batches rather than our model looking at 60,000 images of fashion MNIST data at one time. It's going to look at 1,875 batches of 32, so 32 images at a time, of the training data set, and 313 batches of 32 of the test data set. So let's build a training loop and train our first model. Woohoo! So I'm going to write out a few steps actually, because we have to do a little bit differently to what we've done before. So one, we want to loop through epochs, so a number of epochs, loop through training batches. And by the way, you might be able to hear some birds singing. The sun is about to rise. I hope you enjoy them as much as I do. So we're going to perform training steps, and we're going to calculate the train loss per batch. So this is going to be one of the differences between our previous training loops. And this is going to, after number 2, we're going to loop through the testing batches. So we'll train and evaluate our model at the same step or same loop. And we're going to perform testing steps. And then we're going to calculate the test loss per batch as well. Per batch. Wonderful. 4, we're going to, of course, print out what's happening. You may have seen the unofficial PyTorch optimization loop theme song. And we're going to time it all. For fun, of course, because that's what our timing function is for. So let's get started. There's a fair few steps here, but nothing that we can't handle. And remember the motto, if in doubt, code it out. Or there's another one, if in doubt, run the code, but we haven't written any code to run just yet. So we're going to import TQDM for a progress bar. If you haven't seen TQDM before, it's a very good Python progress bar that you can add with a few lines of code. So this is just the GitHub. It's open source software, one of my favorite pieces of software. And it's going to give us a progress bar to let us know how many epochs our training loop has gone through. It doesn't have much overhead, but if you want to learn more about it, please refer to the TQDM GitHub. However, the beautiful thing is that Google Colab has TQDM built in because it's so good and so popular. So we're going to import from tqdm.auto. So there's a few different types of TQDM progress bars. .auto is just going to recognize what compute environment we're using, and it's going to give us the best type of progress bar for what we're doing. So for example, Google Colab is running a Jupyter Notebook behind the scenes. So the progress bar for Jupyter Notebooks is a little bit different to Python scripts. So now let's set the seed and start the timer. We want to write all of our training loop in this single cell here. And then once it starts, once we run this cell, we want the timer to start so that we can time how long the entire cell takes to run. So we'll go train time start on CPU equals, we set up our timer before. Beautiful. Now we're going to set the number of epochs. Now we're going to keep this small for faster training time so we can run more experiments. So we'll keep this small for faster training time. That's another little tidbit. Do you notice how quickly all of the cells ran above? Well, that's because we're using a relatively small data set. In the beginning, when you're running experiments, you want them to run quite quickly so that you can run them more often. So you can learn more about your data, so that you can try different things, try different models. So this is why we're using number of epochs equals 3. We start with 3 so that our experiment runs in 30 seconds or a minute or so. That way, if something doesn't work, we haven't wasted so much time waiting for a model to train. Later on, we could train it for 100 epochs if we wanted to. So we're going to create a training and test loop. So for epoch in TQDM range epochs, let's get this going. So for TQDM to work, we just wrap our iterator with TQDM, and you'll see later on how this tracks the progress. So I'm going to put out a little print statement here. We'll go epoch. This is just going to say what epoch we're on. We go here. That's something that I like to do quite often, is put little print statements here and there so that we know what's going on. So let's set up the training. We're going to have to instantiate the train loss. We're going to set that to 0 to begin with, and we're going to cumulatively add some values to the train loss here, and then we'll see later on how this accumulates, and we can calculate the training loss per batch. That's what we're doing up here. Calculate the train loss per batch. And then finally, at the end of the loop, we will divide our training loss by the number of batches so we can get the average training loss per batch, and that will give us the training loss per epoch. Now, that's a lot of talking if that doesn't make sense. Remember, if in doubt, code it out. So add a loop to loop through the training batches. So because our data is batchified now, and I've got a crow, or maybe a kookaburra sitting on the roof across from my apartment. It's singing its song this morning. Lovely. So we're going to loop through our training batch data. So I've got for batch, comma, XY, because remember our training batches come in the form of X, so that's our data or our images, and Y, which is label. You could call this image label or target as PyTorch would, but it's convention to often call your features X and your labels Y. We've seen this before. We're going to enumerate the train data loader as well. We do this so we can keep track of the number of batches we've been through. So that will give us batch there. I'm going to set model 0 to training mode because even though that's the default, we just want to make sure that it's in training mode. Now we're going to do the forward pass. If you remember, what are the steps in a PyTorch optimization loop? We do the forward pass, we calculate the loss, optimize a 0 grad, loss backwards, optimize a step, step, step. So let's do that, hey? Model 0, we'll put the features through there, and then we're going to calculate the loss. We've been through these steps before, so we're not going to spend too much time on the exact steps here, but we're just going to practice writing them out. And of course, later on, you might be thinking, Daniel, how come we haven't functionized this training loop already? We've seemed to write the same generic code over and over again. Well, that's because we like to practice writing PyTorch code, right? We're going to functionize them later on. Don't you worry about that. So here's another little step that we haven't done before, is we have the training loss. And so because we've set that to 0 to begin with, we're going to accumulate the training loss values every batch. So we're going to just add it up here, and then later on, we're going to divide it by the total number of batches to get the average loss per batch. So you see how this loss calculation is within the batch loop here? So this means that one batch of data is going to go through the model, and then we're going to calculate the loss on one batch of data. And this loop is going to continue until it's been through all of the batches in the train data loader. So 1,875 steps or whatever there was. So accumulate train loss, and then we're going to optimizer 0 grad, optimizer dot 0 grad.